Thanks everyone for coming. Before we get going, I'd just like to do the acknowledgement of country. So the University of Queensland acknowledges the traditional owners and their custodianship of the lands on which we meet, and we pay our respects to their ancestors and descendants who continue cultural and spiritual connections to country, and we recognize their valuable contributions to Australian and global society. So thanks everyone, and welcome to the, I guess it'd be the fourth Complex Orebodies meeting. I'm really that we're coming to the end of a great year in terms of projects and external support. Thanks for coming along, Neville. I wasn't sure if you're going to be able to make it. Oops, I better hit the timer. I'm going to use a timer today so that I don't run over time. And so what I wanted to do was just give a little introduction to set the scene. The idea was a little bit different this time, in that we're not sort of doing short talks on every single topic. We're spotlighting things a little bit more, but I might just run through a few things. So this is from a paper where Eleanor was the main author, that kind of, I think, sets the scene quite well for the Complex Orebodies Challenge. And that is that the world is looking at a source for metals that's becoming more and more important. But in order to obtain a metal supply from that source, we have to negotiate and in a socially acceptable way deal with a whole series of challenges that aren't related to our technical strengths. And as an industry, that's proving to be a great challenge, and it's certainly an important research topic, and it's really what we're focusing on in this effort. So what I'm going to start with is actually the slide that we put up 4 years ago at the start of the Complex Orebodies program. And again, what that just shows is that, you know, we have this mineral supply of the future from new discoveries and operating mines, and we have to obtain that supply. A lot of that supply is held back by the fact that it can't be put into production due to technical challenges, political unrest, social outrage, environmental barriers, etc. And the aim of this program is really to study a range of things, and this is a range of topics that we talked about at the start of the program. You know, we'll see during the course of the day that our understanding of the program, or understanding of the problem, has evolved a lot, and the mix of work that we're carrying out as a result has also evolved a lot. But a lot of the core, you know, the main sort of core effort is still the same, and that is that for these complex ore bodies that can't be put into production currently, you know, what's the mix of challenges faced by those deposits? What do we have to do in order to arrive at solutions that can allow those deposits to be put into production? And what's the relative value and impact of possible innovations that can address those challenges? And of course, I think probably everybody in the room is sick to death of seeing this slide, but it really sets the scene for copper deposits. And that is that, you know, we've got about 1 billion tons of copper metal that's currently not in production. Most of it was discovered more than 20 years ago, up to 110 years ago. And the reason it's not in production isn't because of technical challenges, it's because of other challenges. And, you know, when we look at copper supply, and I guess I won't go through the bottom ones here, but one of the points, you know, that goes along with that is the fact that we have plenty of copper, we have plenty of most of the commodities that we're after. The problem is more that discovery rates are decreasing, and our ability to put those deposits into production is under challenge. And that just reinforces that when we look at projections for future demand for a whole range of different commodities. And that's related to growth in population. It's related to the energy transition that we're having to go through. That's increasing demand for copper and a whole range of other traditional and non-traditional critical elements. And I guess Eleanor is going to spend more time on this, so I won't spend too much time on it. But if we look at risks across a whole range of different viewpoints, what we can see is that the deposits that aren't in production are facing a range of risks. And this is again a diagram that's shown a lot now, but it shows that for the top 40 undeveloped copper deposits, actually the second one there is now in production, so we should take that one off. But all the red and orange boxes there represent deposits that have relatively high risk under a whole range of different categories. And so again, Eleanor is going to spend more time talking about this, but it's a real challenge. And the other thing that's interesting is that in the course of this year, I had to give a talk, or I gave a talk to the OZIMM in March, and one of the points I've tried to make a few times is that the challenges we face now are different to the challenges that we faced, say, 50 or 60 years ago. So I thought, well, that's great. I'll go away and find a paper that talks about the challenges we faced 50 or 60 years ago. And then I'll be able to say, look, all the challenges were relating to efficiency and dropping production costs and a whole range of hardcore business factors. And who cares about the populace? They've just got to get with the program. So I found this paper in Science written by a metallurgist who is a distinguished professor at Virginia Polytechnic, director of the US Bureau of Mines. He wrote this in 1968 when I was 7 years old. And his first point was our resources are limited less by the amount of raw materials than by the technology of treatment and extraction, by our capacity to produce at a reasonable cost. Well, that makes sense. Then his next one was, but mounting public protests against alteration to land surface and past failures to restore mine lands are going to reverse the trend of large open pit mining and large operations because of a loss of public support. And we can't treat the problems of mineral supply apart from environmental degradation stemming from mining, treatment, or use of any mineral substance. And he also pointed out that if we're not careful, we might run into a problem with CO2 as well. And that we should try to recover metals from mine waste and try to minimize mine waste in any way that we can. And then he finally said, but nobody's going to do anything about it until it's almost too late. So good on you, Walter. Basically, he foresaw a lot of our challenges. So there are some things that we're pretty good at, and that is cost reduction. So this is one of Richard Shoddy's great diagrams looking at cost per ton for copper production from 1900 to 2010, going from about $160 a ton down to $10. And so the question is, can we just keep reducing costs to unlock complex ore bodies? And then another one, we can look at froth flotation and go from 1916, where you've got little boxes basically, to 1973, where we've got something the size of a rubbish bin, to just a little while ago, where you can see the people and you can see the size of that flotation tank. And the question is, and the volumes plotted here. So we're going up to 700 cubic meters and more. And the question is, is the answer just to keep making everything bigger and bigger? Is that going to get us over the line? But there's an implication of that, and that is that as grades go down and we produce more and more, economically, what we find is that of course the amount of tailings goes up exponentially. So for copper, that means that every one of those stripes is 1 times the 20th century in tailings, and we're going to produce 9 times the tonnage of copper tailings we produced in the entire 20th century. So I've shown this slide a few times, and that's pretty impactful. And again, it begs the question: are we reaching the end of economies of scale? One of our projects recently, I've been going back and looking at some of the other battery metals. So here's nickel. So copper was 9 times. If we look at nickel tailings, actual and projected out to 2050, it's 29 times. So because the grade's gone down so far, we're transitioning to not only that, we're mining things that are basically stripping great passages of rainforest and producing mine waste that has resulted from quite complicated and not very nice hydrometallurgical processes for extraction of nickel from laterites. So even though the volume of tailings from nickel is only about 1/5 of the volume of tailings we expect by 2050 from copper, it's still a significant problem. So I'm sure there's a lot more that could be said at that early point, but I just wanted to set the scene a little bit for the problem that we're dealing with, and we'll come back to that in a lot of the talks. As I said, the aim today was to actually give people more time to talk in more detail about some selected areas. Later in the day, I'll come back and talk about some things that haven't been addressed as part of this. We also have a couple of panels, so we'll be looking at, well, actually, I'll go through that in the context of the slides I've got. So the first talk will be from Eleanor, and congratulations again to Eleanor for her DECRA, and that's as a result of all the great work that she's done. The first postdoc from this program, and I think a real testament to the progress that we've made thanks to her hard work, looking at risks associated with a whole range of different commodities using non-traditional measures around some of the environment, social, and governance factors that are becoming more and more important. So Eleanor is going to deal with that and probably some other areas around community and social performance. And then we'll pass to Shabir, who is going to be talking more from the point of view of productivity relating to a series of different commodities. And this will be Shabir's first chance to present some of the work he's been doing from within the Institute for Social Science Research, because unfortunately weren't able to make it to last year's meeting. So I'm really looking forward to that. Then we're going to have a panel talking about critical metals, and what we've tried to do in that panel is that we'll have Paul Gow, who's going to be talking from a source perspective, James Vaughan, who's going to be talking from an extraction perspective, and Lynette Molyneux, who's going to be talking from the perspective of somebody who's been advocating for a downstream industry. She's from the Center for Policy Futures, and James is from the chemical engineering. So all, I guess, a range of different perspectives on critical metals. And then Alice is going to update us on what is, I think most people would agree, is one of the most important things that we could do if we can just work out how to do it, which is to stop all these digging of holes and making great caverns in the ground and blowing stuff up and creating dust and all that sort of thing, and just having a nice straw that goes in and another straw that comes out, and sucking the metal up in some way that we don't quite understand yet. So Alice is going to talk about some of our efforts in that area, and then Neil and Pascal and we'll be talking about work that they've been doing on water supply. And I know this is probably a very outdated slide, so it's just one that I had from before. So they're going to be talking about some of the work that's been done on optimization of water supplies in a very important part of the world for copper supply. And then, of course, another aspect of this whole set of problems is to try to create the value we want to create, to try to put deposits into production, produce metal whilst reducing our footprint. And of course, there are environmental and social approaches to that, but another very valid and important approach to that is to try to carry out processing, mining, and so on in a way that allows us to produce the same amount of metals, but using less water, producing safer tailings, using less energy. And so we've got a team of Lisa, Christian, and Marcin who can be presenting on that later in the day. And then Steve is going to be Steve is going to be leading a presentation and then panel discussion on a project that we did with MMG that involved all of the centers in the SMI, and from all the feedback we've got has produced some very, very useful and potentially important outcomes. And it's really almost like a culmination of some of the things that we've been hoping to do for a long time. So it's well worth having a look at. And then I'm going to talk a little bit about the perspective, just a little bit about what I think we've learned and how we might like to take things forward, or how we're now, how at least how I'm thinking about the complex ore bodies problem and how we want to take further work forward in this area. But that'll be towards the end of the day, and what I'm hoping at that time is to also open things up for discussion rather than just hearing my opinion. So that's all I really wanted to say by way of introduction, and by some miracle I'm 4 minutes ahead of time, so I think putting a timer here really helps. But does anybody have any questions or comments or anything? Did you want to say anything, Neville, before? Yeah. Any? I'll stop sharing here. Any? Oh, I should say, if you have questions online, feel free to type them into the Q&A. If you're having any problems, put them in the chat. But if you've got a question, please type it into the Q&A. Does anybody in the audience or online want to ask any questions or make any comments before we move on? If not, we'll move on to. Why am I holding this up? I've got a mic. We'll move on to Eleanor.
So hi everyone, and thank you, Rick, for the introduction. And as Rick mentioned, I've been probably one of the first postdoc appointed as part of the Complex Orebodies Program. So I've been working on this for the past 3.5 years. And I've been fortunate to work with Rick, and while being based at the Center for Social Responsibility in Mining, and also engaging with people from the Environmental Center and the Water Center of SMI. So it has been a truly multidisciplinary project, and I've benefited from working with professors in basically all of the centers of SMI.
Just want to make sure it's on.
Yeah.
Is it on?
How do I? Yeah.
Yep.
Good. All right. So basically I need to summarize the last 3.5 years and then move on to talking about what's coming next. So it's going to be a little bit intense, but I'll try. So first, coming back to the basics, so what we mean by complex ore body, talking briefly about our general approach, how we've approached that research question, and then talking about the list of academic outputs and as well as industry projects, and then talking about what's coming next. So first, what is a complex ore body? So Rick has already alluded to that in his talk. It is a fairly simple slide. Basically, it's saying that we need to consider all of these dimensions and more to understand how an ore body is to be developed, and that some of these dimensions, and basically all of them, they interact as well. So we need to understand those interactions. And a little bit of a singling out what we have called ESG risks, which are risks that perhaps haven't been well captured before, and perhaps that have been more on the unconventional type of studies in the past, but they are much more in the foreground now. When we say ESG risks, so it's not necessarily the definition that is used by investors when they say ESG, because the G part of it is often considered as corporate governance, so issues of bribery and the organizational structure of companies. But we also consider the G from the outside of that complex orebody system. So by including jurisdictions and the quality of regulations, the quality of permitting processes. So it's inclusive of what's external to the orebody. Just briefly mentioning ESGs in the news, there's a lot of mentions of ESG in the news when it comes to the mining industry. Just a couple of examples of ESG risk materialization, where basically the communities and the context around the project has led to significant production disruption. So that's examples of where risks rebound back to the project. And examples as well of investors paying attention to ESG risks. Significant investors that have signaled that they will not invest or that they will divest from companies if they don't show good performance on the ESG dimensions. At the very beginning of this project, we had a closer look at the top 40 undeveloped copper ore bodies. So that was a way kind of to test the role of ESGs and to try and have a first definition of what is a complex ore body. And what we found was that out of 40, some of these projects just didn't have information, so we were not able to just understand from the outside what was going on in there. But we did see that 17 out of 40 had significant delays. So the project had been delayed for a few years. And in many cases, ESGs were contributed to the delays. And in some cases, they were actually the main reason for the delays. So these were the 11 projects that we identified at the time. And I think most of them are still experiencing these issues, and most of them have not been able to move into production. We also looked at, and on the other side, we had projects like Kamuakakula that didn't seem to have, at least from the research, desktop research that we didn't seem to have any issues on these fronts, and this project has since moved into production. We also looked at the entanglement aspect of how ESG tend to co-occur in the same location. So basically, if you have a water scarcity issue, you may also have a community issue because you're competing for that resource with other water users. So that entanglement aspect is something that was very clear from what we looked at. So that was a preliminary work. And then what happened is that we developed this methodology that allowed us to systematically assess for the presence of ESG risk within the context of mining development. So what we did is, on one side, we had access to the S&P Global Market Intelligence database, which gives us the location of mining projects and also information about ownership, about the commodity that's being extracted, about the size of the project and its stage of development. And on the other side, that's where the big part of the work was to assemble risk categories that we identified as categories that were key for understanding those different aspects of ESG. So they were gathered into these different the three ESG dimensions, but we had so 3 environmental, 3 social, and the overall overarching governance, looking at, for example, the presence, the proximity to key biodiversity areas, the water conditions around the site. So is water scarce? Is there too much water around the site that will make it challenging for managing waste, for example? We'll be in the waste dimension. We've thought about seismic risk because it's something that can also compromise the containment of waste. We look at the presence of communities. We look at the presence of agricultural land uses around the site that would be challenged by the development of a mine in that location. So that's just to really summarize, like we have overall used about 25 different indicators that from institutions like the UN, like the NASA, like the World Bank, and also a few academic projects. And we have assembled all of these measures together to make these 7 dimensions, and then assembled them again to produce an overall ESG score, which gives us an idea of the complexity around the project, and it gives us, it situates the project within a context, and it characterizes that context. So it doesn't say anything about the action of the company to manage those risks. It says something about the pre-existing conditions around those projects. So academic outputs first. So that's where the list starts. So the first paper that we published, Rick was leading it. It was about copper. And this is actually not a graph from this particular paper, but it's for this first paper, what we did was to look at the ESG conditions and how the different ESG dimensions co-occur. So on the horizontal axis, you have the number of risk co-occurrence. So if you have 8 risks in total, if they all co-occur together, that co-occurrence number is 8. And so what we found for copper and how reserves and resources of copper were distributed around the world was that, as you can see, like the highest, the concentration of reserves and resources seem to be between 4 and 6. So, and we set that above 3, basically that's characteristic of a complex ore bodies that have several risk dimensions coming together. And we also looked at the average grade for these deposits. So I think the interesting part about this graph is that you have the highest grades also in those 4 to 6 risk co-occurrence number. So it was looking at technical challenges, which a high grade would make the ore body more easily extractable, but also those facing those ESG challenges. Then the next paper was a methodology paper. So it was really positioning our approach within the larger methodology around critical minerals, supply risk, and seeing like what are we bringing new from these existing methodologies. So when we look at critical minerals, these are methodologies that are often developed by and for countries that are big consumers of metals and minerals, and they want to know what is the risk of supply disruption for these commodities. They want to know their vulnerability to supply disruptions, so how badly they need those minerals. And they also want to know about the embedded impacts that are associated with supplying a particular commodity. So the impacts that are carried through the supply chain and end up being embedded in the final product. And these methodologies, they usually, when it comes to impacts, they usually talk about environmental impacts. That's so CO2 emissions, water toxicity, human toxicity, this kind of, or health impacts as well. So what we were discussing in this paper is how our approach is contributing to that from a different perspective, so more from a producer country perspective. So we're talking about what are complex orebodies, talking about source risks. So source risk being the risks at the source of the supply chain, so in the extractive industry, and how that particular first stage of the supply chain matters in bringing minerals from the ground to actually entering the society. And we talked about ESG risks, and we talked about the idea of situated risks. So the idea of pre-existing risk conditions that are found in the context of mining development. And we added, so it was contributing to the idea of supply risk, but also contributing to the idea of embedded impacts, because either ESG risk, they result in production disruption and therefore they affect supply, or sometimes they don't because risks are externalized and they are being felt by the local context, by the local community. So it's both about supply risk and it's about embedded impacts. And we had that social component as well, which criticality methods usually don't have. So as I said, it was that mix. So basically providing a new view where mineral criticality studies were mostly from the consumer side. Our methods was more on the producer side. So a consumer country would ask, what are the minerals we need? What is the likelihood of a supply disruption? Whereas the producer side will ask, how can we meet future demand? What is preventing us? What are potential constraints to us meeting this demand? What are the challenges that the industry is facing? So there are very different questions. Then, so after really settling this methodology, we had a few other papers with different themes. So a couple of papers were about tailings dam failures. And for one of these papers, we used our ESG framework as a way to filter projects that had this high complexity and zoomed in on these projects to look at what was going on with their tailings. So we were looking at satellite imagery, we were looking at elevation profile, we were looking at the presence of communities downstream of the tailings. So it was in an integrative process where we were testing the presence of complexity around the projects and as well as the risk for disaster and tailings dam failure. I won't go through all of them. So then the one that Rick already had a slide on it, so you'll probably recognize the draft, was the paper published in Nature Communications, which was very topical in the sense, and I think many reports published now are talking about it, is about the metal requirements for the energy transition. So we were looking at metals that are needed for essential renewable energy technologies, as well as the major metals that are needed for the infrastructure around the new energy systems. So basically what we did, so that was one of the main figures of that paper. We looked at the different ESG risks and how they accumulated across one commodity. And we ranked these different commodities in terms of, so at the top was platinum and cobalt, where 84% and 70% of reserves and resources were in a medium to very high risk context when you take the cumulative ESG score. Then what we did is we looked at those ESG profiles face to face with what is expected in terms of future demand. So on this part of the graph, you looked at how demand was going to increase in the future. So basically from now till 2050, how fast is the demand going to increase? So these are typically the specialty metals that haven't had a great demand in the past, but where the demand is expected to grow very fast. So that means that the resources sector will feel that growth and new mines will open as a result. But the important part, I think, was also to highlight the importance of major metals that have already been mined a lot. And so when you look at the comparative demand between now and in the future, the increase doesn't seem too big. But when you look at the overall material movements that will result from the demand associated with the energy transition, you find that copper and iron clearly dominate the other metals. So it means that for these mines, for these commodities to be used in renewable energy technologies and systems, you will need more mines, you will need bigger mines. So in terms of the disruption at the extraction level, they are the metals that will create the most change and disruption. So that's it for the academic outputs that I'll present for today. I also wanted to mention the industry projects. So we have applied the methodology to multiple industry projects. One of the approach was to do a portfolio assessment. So we've compared the portfolio of a company with the portfolios of other companies to kind of compare how these companies were exposed to these situated ESG risks. So basically, we had the list of assets, and for those different lists of assets, we applied the ESG risk framework. We also, in some cases, we did this plus the tailings risk verification as well, which was from the paper that we developed on the topic of tailings. So having that ESG filter and then looking at those tailings facilities on top of that. So that's the portfolio assessment. Then what we also did was the ESG risk benchmarking of mining projects. So having one mining project, typically an early stage project, where they want to do due diligence and looked at how this project compares to their peers. So for example, if you have a gold project, we can compare it to other gold projects at similar development stage, for example. That would be an example of peers. So different kind of peers that can be used, and then you can compare that mining project with the peers. So as a way to look at how complex the development of that project might become in the future. And then finally, we also used that methodology in the research consortium on the social aspect of mine closure. So that I'm pointing it out here because I thought it was an interesting project where instead of looking at ESG risk at the project level, we looked at the cumulative aspect across a region. So we looked at how many projects were in that region and looking at how that results in complexity at the regional level, and with the mine closure filter as well. So understanding that when these mines close at the cumulative level, stage for the region, what will that result in? So so just to finish, so just gathering some of the key takeaways, I think, from the last 3 years and a half. I think so. The complex orebodies approach has really helped us comprehend the complexity of mining development and has really brought a new way of thinking using, and we've added granularity. So a previous assessment, supply risk assessment, they're all using data at national level, but the great input that we add was to really look at high resolution and geolocated mining projects. And considering, so we've used all of these proxies, considering that there is no such assessment out there in the mining industry regarding ESG risks. We are in a context of quite low disclosure. So using those proxies was very powerful to overcome that lack of information generally about the mining industry globally. And as I mentioned as well, I think this is an important step for projects in early stage that want to compare themselves to other projects and see whether these other projects have been able to overcome their challenges. So the peer comparison and being able to use this approach as a due diligence step early on is, I think, a powerful contribution. Remaining challenges, so of course, so there is further ground truthing needing, and we need to also look at what's happening, gather project level observations. But how can we do that when we've been working with 5,000 projects, 10,000 projects? It's hard to check them one by one, and the fact that we have worked with latent and pre-existing risks. So the question of how do these risks materialize, when, and what's the consequence of that materialization? So that's what brings me to the next step. So I think so, just going quickly, so we will be doing further ground truthing for particular research projects. So we have potentially a PhD student who will work in the Chilean context. We have a project with the Pacific Islands, so opportunities to ground truth. But obviously, this requires a lot more work. And if you wanted to do that for the whole globe, you will probably need to have many more research projects to do that. And we are also starting a special issue, so that we'll be publishing. We have invited authors to comment on our work and to bring their perspective into that special issue. So we will have people, authors that we've invited, contribute from their discipline to comment on our work. And I think that will also identify avenues for future research as well, and collaboration. And then talking a bit more about the DECRA. So the DECRA is really a continuation of the work that I've been doing over the past 3.5 years, because I guess the base assumption of the Complex Orebodies program was to understand, to say that source risks around mining projects, they can result in supply risk and as well embedded impacts, as I mentioned earlier. And what my project will do is keep testing that assumption. And how I will do that is I will again rely on those global databases and the database of mining projects to extract a certain set of projects where I will be able to one by one check them. I think with the frame I have in mind, I will be able to have information, qualitative information about 1,000 projects worldwide that I will select with the help of some research assistants, and looking at, and there would be projects where ESG risks have materialized for the project. So it's looking at different events that are happening at the interface between the project and between the community within the context in which the project is developing. So it's the idea of outbound risk. So when the project generates risk for the community, and inbound risk when those risks rebound to the project. And I guess some of the questions I will ask were, when these risks materialize, who is at risk? Like the question of risks to whom? Is it mostly the project that is affected? Is it mostly the community? How often do risk bounce back to the project? How often does it result in supply risk? Whereas how often does it result in embedded impacts that will be carried through the supply chain? And then feeding this information back into the global analysis. So ultimately having a global atlas of these projects. That would be documented. So that's it. So that's my project for the next 3 years. Thank you. Sorry.
Thanks, Eleanor. So we have one question on, I'll go to Alice first and then come back to the one online.
Thanks, Eleanor. That was a great talk. I'm interested in a comment that you made at the beginning, which was where I think you said that investors' learning and understanding of ESG is different to ours. And I'm wondering if you can expand on that and just sort of help me close the gap of where that understanding is different, because investors, especially activist investors, are starting to have a pretty big impact on things. And also what you think we might need to do to close that gap.
Thanks, Alice. I think the main gap is in the G dimension. So it's just because I guess when an investor wants to look at the ESG performance of a mining company, they want to look at what the company is doing to manage the risk. So that's why investors, they see that governance side as corporate governance only. Whereas for us, because we didn't have access to the information of like internal industry workings, we took that approach of external risk, the idea of situated risk. So basically, we try to gather as much information as possible about what's around the project, rather than looking at what the company is actually doing on site, because of the lack of information. But for the environmental and the social aspects, I think there is much more overlap there. What I would do to fix it, I think with my new project, I will have the opportunity to look a little bit more deeper about what actually happened. And so it will be not only the context and what was going on in the context, but how did the company interact with that context? So it would be much more double-sided. So that should help fill that gap a bit. Thank you.
Okay, so we've got a question online here from Alan Levitt. Thanks, Eleanor. Does your work give you any insights into the key advancements needed to reduce ESG risks? So for example, would reduced environmental and water risk / damage flow on to reduce social and governance risks?
I think you may have a better answer to this than me, Rick. But I think it's the powerful aspect of this project is it has helped us really comprehend the different dimensions and understand that very often they work together. So I think what it has shown is that there's probably not one solution that will be identified in one dimension that will help fix the other dimension. So it's really a call for adding or having much more multidisciplinary collaboration within mining companies so that they can communicate between these different dimensions and identify solutions together. Is there anything else, Rick, that you think I should mention?
That's exactly the answer I would have given. So the reason we did all this work was to understand better what the mix of challenges was, leading directly into the research that we're carrying out to come up with solutions to those challenges. So how much time we got left on the
1
timer?
minute.
1 minute. We've got time for another question if anybody has one online or in the room. If not, okay. Thanks again, Eleanor. So we're now going to move on to, actually, while I talk, I'm going to change some batteries because I can you guys hear this online? I'll just keep an eye on this. I think oh no, it's all right. So we're now going to move on to Shabir Ahmad, who's from the Institute for Social Science Research, and is going to bring a very different perspective to the sort of work that we've been doing, but a very valid and useful one. And so Shabir is going to be focusing on complex ore bodies, socioeconomic development, innovation, and productivity issues. So I'm just going to bring up your wake up, everyone. The timer is going. Why is that still? Oh, right. Okay. Presentation. It's on. Yeah, that's on. Okay. I'm gonna make that. It's all yours. Thanks, Shabir.
Thanks, Rick, for giving me an opportunity to just share my thoughts today. Good morning, everyone. I met Rick, I think 3 years ago, and when he was, I think, in the middle of just finalizing his first paper, what Eleanor was presenting on the ESG framework. And we have been in discussion, and I wanted to I was quite interested in the way they were looking at this different risk and their, these implications. But what I just noticed in that, so basically, there were further potential to work on that in an looking into an economic lens, basically. And the second thing, what I was just working for, I've been thinking for some time, that was the productivity issues, which is one of the, I think, core in economics perspective. So that was the basically start of the discussion. but we have been in discussion for 3 years, and I was able to formalize it from the last year, but unfortunately I couldn't make it in the last presentation due to some unavoidable circumstances. So I've been working on this issue since then for the last year. I'm spending about 20% of my time there. So there was so should it go?
I don't know. So we can either use the mouse or just the arrow keys.
Okay. Okay. So as I mentioned, so there were two areas I wanted to focus. The first one is the ESG risk assessment, what they have done already. What I have noticed there, so actually they are certainly very important in order to measure those inequalities and just to map those risk factors. But the way that has been done so far, it gives you the point estimate. Point mean that is just you have a fixed value. But when we discuss, we think in terms of the mining perspective, there are uncertainties. There are huge uncertainties. So I wanted to bring those uncertainty into those risk factors. So when we talk about the uncertainties, it means we have to look into the confidence intervals in terms of quantitative analysis. And there are different ways to do that. One is that basically you use the prior information. You have the prior information about the risk. You incorporate those, and then you draw the posterior information. That is what we call the Bayesian analysis, which allows you to incorporate those uncertainties and just construct the intervals, the range where the risk can lie, rather than just looking at a particular point. This work I have not, finished yet, but today's focus will be the second part, which I have been doing so far. That was the productivity analysis, the complex or those productivity issues. So this topic has been on the limelight for many years. Researchers, policymakers in industry, they are always concerned about the productivity issues. So what are the sources of the productivity? How that mineral or the mining productivity can be increased? So there are there are many those measurement issues. So I'm trying to overcome those issues with basically using the data of 7 complex ore bodies. I have got data for 30 years, mine level data for the production, for their cost of production. These include cobalt, nickel, zinc, copper, gold, silver, and platinum. So that data I have been using, and my presentation will be in that has basically 2 parts of the analysis. But the first is just for the demonstrative purposes, which I'm still working on. But the second is almost the finished one. That is just gold sector data, which we are just aiming to finalize the paper by the end of this year. I was aiming to submit by before 30th of November, but I had to do some more analysis. So since we met last time. So when we talk about the productivity, there's a partial productivity and the total factor productivity. The partial productivity, basically, when we talk about the labor productivity, the capital productivity, the energy intensity, these are the partial productivity indices. They give you some idea how about the performance of any output produced, whether it is mineral or agriculture or any other output. But yes, that is, from the theoretical point of view, yes, these are very helpful, and from the policy perspective as well. So for example, marginal productivity or the partial productivity basically will allow you to identify, for example, if you are taking into account the emissions, so the emission intensity. But so there are some limitations. You cannot paint the overall picture when you talk about the productivity. So there are other sources. If, for example, there might be divergence when you talk about the productivity, labor productivity might be increasing, but on the other hand, your carbon emission or intensity is increasing. So that is basically offsetting your productivity. So we have to take into account those all factors simultaneously, basically. That's what we call the total factor productivity. And then, so that can be decomposed into different sources that could be, there could be the innovation and the technology that is driving force for the productivity, which is basically now believed in the mining sector. There are some environmental factors. There are several other factors basically which we talk about. I will just discuss just after this slide. So here I'm just giving you a very basic concept of what is productivity. Productivity is basically is the ratio of the output to input. Usually people confuse the profitability with the productivity. Profitability is the revenue over cost, the first equation. Price into the output produced, and the the input prices into the input quantities, labor, capital, materials. And if you split that one, can I use that one? So, no, okay. So if you want to split that, if you split that equation into two parts, first is Q over X. That what it is saying, TFP second bullet point is defined as the ratio of an aggregate output to aggregate input. The first part is the productivity. The second is the term of trade. So the profitability overall, so it's not the productivity, it's basically encompassing the productivity, but the term of trade usually is perceived as a productivity, which is not basically, because when you talk about the profitability, that is from the firm point of view, yes, firm wants to maximize the profit, but that is not all. So productivity is more than the profitability in the terms, so that in terms of the raising standard of living, the welfare perspective, to maximize the output with the given resources, or to achieve the given output level by reducing your amount of input, the carbon emission, the capital, the labor, and other. So that's basically the differentiation, how we differentiate profitability versus productivity. So the productivity is the aggregate, the ratio of aggregate output to ratio of aggregate input. But there's a productivity change, how that changes over time. So say, so the ratio of the output in current period and divided by the ratio of output to input in the previous period, that is the productivity change. So that basically the concept I would be using for the analysis I want to demonstrate today. As I mentioned, the first part is just the demonstration of the result, which needs a lot of improvement. The purpose is just to show those results, to seek your input, particularly. So unfortunately, I don't have a background of this. I don't have technicalities in terms of the O grades and how to homogenize the products. That is, I think, one of the main challenge I'm facing at the moment. So, so the purpose is just to demonstrate that. As I mentioned, so there are different drivers of productivity. Innovation is at the core. Everyone is talking about the innovation, from robotics to hauling trucks and whatever. So innovation could be basically one of the innovation in technology, basically, that could drive the productivity. So the price recovery is another source. what I just split into P over W, basically. The price recovery is the, in broader term, we say the term of trades, basically. And then we talk about the best management practices that in productivity concept, we usually talk about the technical efficiency. So how there are different firms, they are using different technologies, how they are able to maximize their production by using those technologies, the skills of labor that comes under technologies as well. So and then we talk about the scale and scope economies, as Rick was talking about the scale production. The scope economies basically is the when you are able to reduce your cost of production when you are producing more than one product jointly, say copper and gold. So this is, you have output mixes, copper, gold you are producing using this given amount of inputs. That is the scale scope economies. That could also be applicable on the input side. So you have input mixes. So you are substituting capital with labor and those. So appropriate input mixes that would also lead toward the scope economies. So this is another source of important source of productivity that should be looked into. Then technological change, and no doubt the environmental and regulation governance issues. So the productivity can be decomposed into all those different factors. So using, I have skipped a lot of equations I mentioned this morning with Rick, because given the time frame, I have all those. If someone have some question, I can just bring later on. But I want to demonstrate, as I mentioned, this is the, these are the 7 commodities which I just use for the analysis. And this is just showing the one of the component, that is the technological differential, that is what the technical efficiency. What is technical efficiency? Technical efficiency is basically a firm, if a firm is able to produce the given level of output by reducing its input. To what extent the firm is able to maximize its production from the given resources, or to reduce its input to get to achieve the given level of output. That is the technical efficiency. That is basically the best practices. That is the technology differences or practices each firm is taking into account. So these results are based on the 30 years data at mine level. So copper, cobalt, gold. So what we observe here, so there's huge disparities within each industry or each metal. So these all are different firms spread across the world, and across the minerals there are disparities. So skewness here. So for example, cobalt is the higher the number here is closer to 1. So more efficient that firm is, or that sector is. Closer, look, the copper is more spread. So if you will look at the median value somewhere here, cobalt is here, and the gold quite spread, but still you can see the technology differences: silver, nickel, zinc, and platinum. So this is basically, as I mentioned, what I used the output produced, and then I used the input labor cost. Then I use the capex. I use the energy split into electricity as well as into fuels. But and then I use this ore as an intermediate output. So what I did, so very crude adjustment measure. What did I do? I just adjusted with the O body with the given ratio of the O grade, the percentage of grade. But I'm not sure if there's any other way just to adjust that O body, because there's a heterogeneity. The O grade is varying enormously. So I think that is affecting the production. So one of the area I'm just seeking the input, how to make those accurate estimates of those ore, or just to adjust the ore body, to adjust the quality of ore in order to translate into the production. So that is basically I wanted to seek your input. So then what I did, then I just translated those number into the change in productivity. So starting from I just split the data into different years. So I didn't use from 1991 just for the demonstration purpose. I started from 2011. So if you look at platinum, copper, and gold, they are with reference to 2011. So there's an increase in gold productivity. The copper was declining, and platinum was also declining over the time. This is the productivity, overall productivity, the change in productivity with reference to year 2011. And then these are, I just picked only two drivers. One was the change in technologies, the technology differentials, what we call the technical efficiency. And the other one was the scale mix factors, that scope economies, scale and scope economies together. So copper is again showing this. So the productivity is basically explained or driven by these technologies. And here in gold, again, the technology is, the scale and scope economies are driving more rather than the change in technologies. So platinum, so there was decline, and again, that was more explained by the change in technologies, the technology differences. So as I mentioned, these are very crude measures, are preliminary measures, but I have to refine it and bring more rigorous analysis in order to basically demonstrate those results at each commodity levels. So there are 7 commodities I have selected so far. So this was just the first part of the demonstration. Then we got the mine level data for 86 gold mines from S&P, and we wanted to look at the environmental effect into the productivity. So we adjusted those efficiency analysis with the environment by taking into account the emissions, basically carbon emissions. So we included this carbon emission as an other output, but undesirable output. So they are, I mean, in the productivity analysis, so we have the desirable output, that is the good product, that is the production of the gold. But so carbon emissions are jointly produced, waste is jointly produced. So we have to take into account those factors as well. So economists and researchers have devised or proposed different measures how to account for those undesirable output. So what I did, I used those one of the methodology that is called the radial, basically distance function. So either you contact your input radially in a certain direction just to achieve the maximum level, or you increase your output radially from the given output input level. So 86 gold mines, what we because they are using the different types of technology, we divided into 3 different categories. Those are open pit, underground, and the combined. So these 3 technologies they are using, and we estimated 3 different frontiers, constructed 3 different frontier for each kind of the mine operation, and then we lumped together, we aggregated all data, and we estimated a meta frontier. And then what we did, we wanted to see this differential. So this black line is showing the meta frontier. So you are just taking all 86 those funds into account and just estimating that frontier. Then the group 1 is, say, that is the open pit, group 2 is the underground, and group 3 is the combined. So any dot point below this yellow line, a gold line, so that is showing the distance from the yellow frontier. It means the firm located underneath that is less performing. They are less technically efficient. Any firm lying on this gold frontier that is the best performing within that, if you just take into account that particular subset of data. But if you just compare it with the meta frontier, then the distance between any point on the yellow line, gold frontier to the black frontier, that is what we call the technology gap. So we tried to estimate those technology gaps, basically. What we observed, there are disparities, huge disparities in the technical efficiency and productivity within the sectors, which range from 0.3 to up to, I think, 100% efficient. But so these are basically the technical efficiencies for the entire sample, then for the open pit, and then underground, as well as combined. So there are disparities, they are differential. And then the first column is showing, in technical efficiency, first column is showing without taking into account those carbon emissions. But the second column shows when we have taken into account the carbon emission. So we adjusted the productivity or technical efficiency by using those carbon emission. Then we estimated those technology gaps, which are basically showing with and without environment. So the higher the number, closer this number to 1, it means there's no technology gap. They are performing as equally as the best performing. But higher the number is showing there's a huge technology gap. They are lagging behind. So you can see the differential with those technology gaps for this 86 mines. And this has been translated here. So if you look, for example, this Australia the performance is declining. So this the number is decreasing here. Similarly, if you look at the Canada and Russia and other basically those South American countries, so there has been change. There has been change in the ranking. So we have those ranking basically of all those 86 firms. So the ranking changed significantly when we have taken into account those carbon emissions. So the ranking of those all firms changed significantly. But these are the technology gap, more or less same what we were talking about. What basically the purpose was just to demonstrate those results, and that the second bit is already we have finished our analysis, and soon we will be submitting this for the publication. But what my aim to achieve in the remaining period, so I will continue to refine those productivity estimate for the 7 commodities, and I want to decompose those productivity over the time using those methodology, but with the more sophisticated analysis after seeking input from colleagues. And one of the purpose was just to demonstrate or just to share those with the audience if someone is interested. I mean, particularly have those technical expertise just to refine those outputs and inputs, that would be a wonderful opportunity for me as well. And as I mentioned, I aim to do that analysis at each commodity level for all 7 commodities. Unfortunately, we didn't get any emissions data for all those 7 commodities over the time. So I had been in discussion with Martin at some point, and we did discuss. There was some crude Meyer, but I didn't apply that one so far. I'm still trying to find a way to get the actual emissions data for those commodities, so we can incorporate the environmental factor as well. So that, and then we will examine those all drivers of productivity I have already talked about. And also I aim to estimate those ESG indicator, what have been suggested by Rick and other people. As I mentioned, I want to create those indices over the time and taking into account those uncertainties by using more sophisticated econometrics method, what we call the Bayesian metrics. So I have been, so there were few publications which were not in the mining arena during this collaboration, but they were more around the energy. So I have not included those, but certainly we are aiming those publication out of this one, as we are aiming by the end of this year, based on the analysis I've just shown you at the end. And there are a couple others based on those this analysis, and then I will continue to work on this estimation of this ESG for the publication perspective. This is what I wanted to share with you today. Thank you so much. I've still
got a minute and 43 seconds left. Any questions from the audience, or again online, if you've got any, put them in the Q&A. I actually had one while people are thinking of other ones. So the diagram that you had with the frequency diagram, what are the, when you keep going back?
This one?
No,
that is hidden, I think.
Way back at the start.
Yeah, sorry.
That's all right. If you go back to that one and then reshare or start the presentation. My question was, while you do here, well, I'll get that up. I'll get the one I was after, which is this one. Get out of there. Get out of there.
Yeah. Yeah.
What are the individual points in that? Because you know, you look at
each is an individual point, basically.
Yeah, but it's an individual point.
Yeah. So this is basically no. So this is what we have. Yeah, we have done. Yeah, these are the individual points. But
for mines, are they mines or what are they?
Mines.
Like because with platinum, for example.
Yeah.
There's no way there's that many platinum mines.
No, there are
only 100.
Yeah, there are 300 observations only.
Okay.
Yes.
Yeah.
There are thousands of observations there, but there are 300 something observations because I have just sliced the data from 2011 to
they're time slices.
2020. So that's why platinum is only having, I think, around 300 observations.
Yeah. Okay. Thanks. I'll just turn that one off. There we go. Do we have any other any other questions? You don't have any online?
Yes.
Oh.
Yes.
Got a couple over there.
Yeah.
Thanks, Shabir. On that plot of the it was a map of the world, and it was showing the efficiency of the mining operations before and after, including carbon CO2 emissions. And what was immediately obvious, and I think you pointed it out, was that, for example, the South American mines or South American mines, once you included CO2, their efficiency, or I'm not sure what the measure is formally called, seemed to improve a lot. Oh, here we are.
Yeah.
And Australia's performance appeared to go down.
Yeah.
I'm not sure if you're the right person to tackle in terms of why this is happening, but would you hazard a guess as to why that is happening?
So that depends on, I think what I was just thinking, maybe these are the different operations, underground versus the open pit. So I have not looked into that. That one of the reason might be those are underground, they are, emitting less pollution. And if they are falling under this category, certainly that output seem to be improved there. So that could be one of the reasons, but I have to dig it deeper. Yeah.
Okay, thanks for the presentation. I think it's interesting to try to identify the technology gaps. Just when you showed the plot that Rick was referring to as well, just with the different commodities, how do you take into account or consider that a lot of the commodities are produced at the same time? So if in some cases you have mainly a gold mine, but sometimes you have gold as a byproduct of copper, for example. So how is that kind of
so what we use, for example, this is the output input relationship. If I just go back again, can I just, okay, so it is an input output relationship. For example, it's a production technology. So we have cobalt production, we have platinum production, we have gold production. So we basically converted that production into same units. For example, some were in tons, some were in ounces, some were in pounds. So we converted it into in a common scale. Then we had those inputs and labor capital. So this is the relationship between output and input. So we estimated a kind of the production function. And then that production function was further decomposed into the technical efficiency, into the technology, into the other factors. So there's a technical relationship between output and the input. That is the production technology, our production function we estimate, basically. So how that was performed in the first part, it was performed, so this is performed using a linear programming, for example. So you construct piecewise linear programming in order to maximize production given the input for each one. And then at the end, once you get the score, you get the relative. So you spot the best, performing firm, and then you convert all those scores relative to that firm, and then you can, construct that frontier, how far they are from each other. So that is, I don't know what was the question. Yes, we can have more chat.
Yeah, we can. There's probably we can talk about. We can explain it a little bit better later. Or do it. It was well explained, but we can explain it more.
Yeah.
Okay. Well, I think did somebody else have a question before we? Right. Well, we're eating into morning tea now. So thanks very much, Shabir and Eleanor. So we're going for a break now, and we'll be back at about, a little past 10:40. So we've got about 20 minutes for morning tea. So thanks to our two speakers this morning. Our next presentation is from Alice Clark. Alice has been leading our in situ recovery bio-leach project for the last since the start of the Complex Orebodies Program. And so over to you, Alice. Thanks very much.
Thanks, Rick. Did you have a time thing here?
Yes, I'll put it up.
Otherwise, if somebody could let me know when I'm rabbiting on too long. I really wanted the panel to go for another half an hour. I was absolutely enjoying that. But unable to catch Rick's eye to say, let's just keep talking here. This is very interesting. The in situ leach and bio-leach project, in situ recovery and bio-leach project, the thing I'm going to talk about today is specifically the biologically derived lixiviates for in situ metal dissolution. There's another two parallel projects. which you might find amazing because Rick has very kindly given us an amount of money that we've managed to spend on only 4 people that are up there. Everybody else has donated their time. The collaboration across the university has been pretty amazing. We've got people from School of Earth and Environmental Sciences, Chemistry, Microbiological Sciences, EAT, BRC, JKMRC, and up until recently, Gene Tyson was also part of the team out of QUT. He stepped back until the project gets more into the area of his interest. So the collaboration has been free and fantastic. Just in case there are people who may not understand some of the terms that I'm going to talk about, I'm going to explain a couple of things as we walk through the biologically derived lixiviates project that I'm going to talk about now. And the first one is in situ. In situ means that it is in the place that it formed. It's in its original location. And we're specifically looking at mineralization here, in situ mineralization, and we're concerned about trying to dissolve the valuable minerals or metals out of the mineralized area in and where it is without moving it. So I'm just going to talk through a couple of different ways that we approach this. If I can do the mouse thing, does that work? Yeah, that's good.
And then the mouse thing should.
Next one, yeah. Okay, I've got it back. Okay, so you can approach mining that particular deposit, should it be economic, by open pit. The depth down the y-axis there could be, kilometres or metres or hundreds of metres. It's not really important, but in the case where this might be quite deep, you're obviously taking out a considerable amount of overburden to get to the deposit at the base. In the ore-bearing loads, you're going to have a lot of infrastructure on top and produce tails. So that's a conventional open pit approach. If we wanted to do a surface bioleaching operation, you would take that material and you would form big heap leach pads, and those you might inoculate with microbes. In this particular one here, you'll notice, and I better not do that with the mouse, I think there's a stick. Okay, the old JK stick. Yeah, but I might undo what I did before. I'm stick friendly, but not so much good with the mouse. And so here you've got oxygen being pumped in, a whole bunch of microbes that go in the inoculum pad, which are squirted out or actually mixed in with the material. The lixiviates percolate through, and this is the pregnant solution that's draining around the blue on the outside, goes to solvent extraction and electrowinning. And there's a number of these operations that have been going for decades in terms of surface bioleach. I went to visit one with the team that I was working with, about 5 of the guys on that first slide, back in 2019. And this is a legacy heap leach pad in New South Wales. It's not a particularly big one. There's about 8 of these. They go for 1 kilometre or 2 one way and about half a kilometre the other way. As I said, not a particularly big one. There I am for scale. And this particular heap leach pad is probably started about 30 years ago and finished maybe 10 years ago. And now every time it rains, it belches out an amazing amount of acid mine drainage. And people in the room are nodding, so they're very familiar with this, but others may not be aware of what happens to legacy pads. So hence the drive for us under the Complex Orebodies program to try and find novel and different solutions for these sorts of things. If you were to have an in situ leaching operation, and these exist, uranium is mined this way, there are a number of copper operations, not so many gold. What you would see is considerably less surface infrastructure impacts. In this one, and I'll grab the JK stick again, you'll have what's predominantly acid being pumped down these blue lines here. there might be some form of fracking or preconditioning of the ore-bearing formation at the bottom to allow the acid, or it doesn't necessarily have to be acid, but in this particular example it is, to allow it to percolate through, dissolve the minerals into metals that you're interested in, get sucked back up the pink and goes through to your processing plant. There's monitoring wells out here, which are really looking to make sure you're not losing the valuable stuff, but they're also picking up if you've got some environmental damage happening in the stratigraphy in between, because there'll be water channels and other things that you might be impacting there. Okay. So the one on the right-hand side is, you know, better, but still environmentally risky. And the one on the left-hand side is probably no longer where we need to be thinking if we're moving into the future. And what we're really looking to do is to get out that bit down there with nothing looking different after we've finished. So the objective that we have in our program there is to discover novel enzymes or bioengineer proteins or complexes of proteins that can have either evolved naturally or can be engineered to selectively leach primary chalcopyrite. And I'll talk about why we went down that path and in a moment. And the reason why we think we can do this is because these microbes, they exist in nature within living organisms, and they perform very rapid oxidation of iron-bearing molecules. In fact, it's 10 to 100,000 times faster than chemical reactions. At University of Queensland, we've got the expertise to grow and evolve these organisms that have the potential to do this. And we also have the expertise to bioengineer proteins to perform a very desired and specific function more rapidly than they might be doing under their natural activities. We wanted to do this because we wanted to eliminate the use of acid. We also wanted to eliminate the use of organisms. You have to keep them alive. They need oxygen, they need to be fed, they need to be in certain temperature ranges. And that gets annoying when you're on a heap leach operation and everything dies. And we also needed to find something that was environmentally friendly. And we're really keen to move into the space of tailings, but we'll start that next year. To do this, we had to have a deep understanding of the biological organisms that leach metals, probably more so than the science at the time 4 years ago had published on. We also were really interested in the fundamentals of copper oxidation. Everybody understands copper oxidation, but what we were interested in is when is it chemical and when is it biological at a nanoscale? And so that was part of the investigations that we went through. We also needed to understand our target environment, and this environment might be deep, it's anoxic, it might be acidic for other reasons, there'll be gangue minerals, there's a whole bunch of things in the environment of that in situ ore body that would impact on what you would work back to find the appropriate solution. So we wanted to find a new lixiviant, and we're not at all interested in the engineering aspects of getting it down there, of permeating the ground or getting it back up. That was just outside the remit. Okay, so on the right-hand side of this is a scanning electron microscopy, a word I've never been able to say properly, image of Shigella and onadensis, which is a bacterium. Now, this particular bacterium is notable because it can reduce metal ions in a variety of environments, both with and without oxygen there. So that one's pretty neat. The other thing that's interesting about this is if you can see these little nano wires, and I noticed them on a slide, Paul, that you had as well earlier, and I wasn't quite sure what the bacterium was there, but you see these little nano wires here. They carry electricity super fast, and NASA's currently looking at those for the ability to produce electricity in space from bacterial coated surfaces. We're interested in them because redox reactions are electrically competent reactions. And so we're interested in finding out exactly how electrons travel along those and what role they play in redox reactions. I've also listed up there a couple of other candidates for the bacteria that we might be looking at later, but this particular one had the nanowires in it, so I put that up, and it is used in some copper biomining operations. But more commonly used, and this is a transmission electron micrograph of I'm just going to call it A, ferrooxidans, which is a very common microbe that's used in the reduction of primary and oxide coppers in biological heap leaching. The one on the right-hand side is growing on a primary sulfur for prill, and so you can see that they're all having a party over there. And on the left-hand side, it's just growing on a sulfur crystal, if you like. So not so many of them over there. And that's important because microorganisms, and in particular bacteria, survive by getting nutrients from the substrates that they live in, and they adapt really quickly to the substrate that you've given them. So they evolve very rapidly, and you can see that the ones over here and compared to the ones on the other side are looking different, even at the level that you can see here. So we intend to use that ability to evolve in some of our work with bioreactors next year. So they survive by breaking down chemical compounds, and they attach or come into contact with substrates that have the chemical compounds that the individual bacteria needs to survive. But during that process, those redox reactions that occur and the electrons that are transferred through the cell membrane are particularly interesting to us. So for our project, we're looking for biologically derived lixiviates, and we're interested in where those microbes break down chalcopyrite. And we're particularly interested in the actual mechanism of that breakdown rather than just knowing that it occurs at this scale. So to do that, we need to look at the innards or take a pretty detailed look at the makeup of microbes that consist of a specific protein chains that we're interested in. So proteins are made up of hundreds or even thousands of smaller units, and they're called amino acids. And these are joined together by something called a peptide, and they form very long chains. And these are biological compounds called proteins, but there's subsets of those that we're interested in. Now, some proteins are really specific to what they do. So that structure absolutely determines what a protein will do in an organism or a living cell. Some of the proteins will convert the substrates that we're interested in. Others will take nutrients around the cell or around the body to a particular place, and others will get rid of waste products, so oxygen, energy, etc., to where they're needed inside the cell. I spoke a minute ago about amino acids, and these are really simple until they're combined together to form these extensive molecules that undertake all of the work of living organisms. So this one here is a group of amino acids that are joined together, and this is the hemoglobin protein. Most people are familiar with the hemoglobin molecule. It's long and complex. But you'll also notice, I think you can see in the middle here, oh, my mouse isn't pointing, sorry. You'll see an iron atom in the middle, and this is a globin around it, and these are the hemes that sit around the outside. And that's what gives your blood the red color. You'll note also that, well, you'll know, I guess, from just knowing a bit about your own body, that hemoglobin takes oxygen from the lungs into tissues and organs, and it also carries carbon dioxide back from the lungs. And it does this by having unstable electrical bonds on the outside as it's carrying this stuff around your body. And it's those unstable electrical bonds that we're really interested in when we start looking at the protein strands in the various complexes that we want to use for mining. And it's possible that we will be able to engineer things once we understand this. So I'm going to then go to the way that protein engineers look at these. And I picked hemoglobin because it's Christmas time and there were a lot of Christmas colors here. And also it wasn't one that we use in biomining. So the concepts were a little easier to work through. There's something called a heme here. I mentioned that before. And I don't know if you can see the detail, but there's 4 hemes in hemoglobin. And these are these green globs that are in here. And the rest of the amino acids that sit around the outside.
You might have heard of sickle cell anemia. So a protein engineer will look at just that picture and know that that is hemoglobin. And really good ones that go into splicing and dicing and making what I call Frankenbugs will be able to see just by this picture that somebody might have a blood disorder. And now you start to think about how you might be able to engineer and reconstruct these things to fix those. So if we take the next step and we take that ability and learning into what we want to do, you can start to see that the possibilities are there for applications in the mining industry. Okay. So now we all understand everything about proteins, amino acids, and these complex functional protein strands that conduct the work of a living cell. And we've got some dangerous pieces of information because we can make ankle deep leaps into the future of what we might be able to create with this knowledge. I want to focus now on a very special subset of proteins called enzymes and a subset of enzymes called cytochromes. So between these two classes, almost all of the chemical reactions that take place in cells are undertaken by enzymes. So enzymes are just special proteins and amino acid complex. They work with cytochromes to affect this electronic transfer and redox reactions and also transfer energy within the cells to and from electrons that are grabbed from redox reactions with the substrate. Now, because microbes evolve very differently depending on the environment that they've been grown in, which we saw in the micrographs before, it's possible to actually grow microbes to do a specific thing or behave in a certain way just by adjusting the environment in which they grow. And this understanding led us to consider what we could do either by evolution through environmental engineering in a bioreactor, or protein engineering by direct splicing of a suitable protein to potentially deliver an abiotic, so outside of a living organism, extracellular string of enzymes and cytochromes to leach copper in potentially a chalcopyrite mineral. So to me, this looked like fundamental research. But when I started working with the protein engineers and the genomics experts in Cs and other parts of UQ, they said, no, this is done all the time. It's not fundamental research at all. It's very applied science. And it just goes to show you what happens when you step outside your area and you start working with other experts. Where we do need some help, though, is on the leaching chemistry. So we'll be reaching out to some leaning in for that. This is rustacyanin, which is chosen for testing. Those in the game don't call it rustacyanin from aferrooxidants. They just refer to it as rusty. It's really well known, and it's been shown to have incredibly high reduction potential and can therefore very effectively oxidize iron. Our hope was that we could take rustacyanin out, and that's that blue one in between CY2 and CY552 and CA1, which are cytochromes. So we were going to take this as the enzyme here. Cyanin's the enzyme, and these are all cytochromes, which work in conjunction with rustacyanin to move electrons around. Our hope was that because rustacyanin was doing the heavy lifting of shifting the electrons around, we could just snavel it out. Interestingly enough, its little metal ion that makes it active is copper. That was nice, a nice bit of synergy there. And we could take this enzyme and we could have it exist outside and attach it to an electrode, zap it, and it would be able to start to break down the iron sulfur bonds that sit in the chalcopyrite crystal. However, the results were somewhat disappointing. It didn't like being attached to an electrode outside the cell, and it kept falling apart. So then we thought, well, that's fine. We'll try it in a media that it might be more happy in, more like being in its cell. And that didn't work either. It couldn't connect with the electrode part in the fluid, and so that didn't work. And then we just decided rustacyanin did not like working without his friends, the cytochromes. So then we thought, well, that's fine. We'll go and we'll take the cytochromes out. We started with CY552. We attached that to rustacyanin, but it turns out that taking the cytochrome outside and trying to reproduce it, they fold. So they fold in particular ways. They don't always fold the right way. That's how you end up with things like sickle cell anemia. And it didn't fold the right way. And then we bought something called a chaperone to bring in, and a chaperone will help the things fold the right way. And that didn't work either. So then we decided that perhaps it needs the whole complex, and things started to get a little bit testy because we ran out of money. How close we were, Rick. So what we then decided to do was to take the remainder of the year and try and work out the comparative leaching experiments in beakers, if you like, to say, and James alluded to this before, make sure that you have a value proposition and that you know what's happening on the outside, so that when you go and take it to market, you have something to show. So we started to perform the leaching operations on the outside while we were working out what to do with this set of proteins that just wouldn't behave the way that we wanted. And in the meantime, started looking back through ancestral protein groups to see if we could find one, because the Earth has evolved for a long time. And looking back at ancestral proteins, we might find one that had existed in a place in the past, and the massive databases that are held, to pull that in and reconstruct it from there. So that piece of work kept going over here. And over here, we decided, well, we've got some data on how quickly it worked. Let's see how that goes with different amounts of acid in different chemicals in there, which I think I rang Rick up one day and I said, we've just discovered that acid leaches primary copper. And Rick said, good, not good. We've known that for many years in the industry. But it was very useful for people in that part of the experimental process to actually prove that to themselves. So in looking at the cytochromes, we had a lot of trouble with the folding and unfolding of those, and that proved too difficult as well. So we then moved to the point where we thought, okay, what are we going to do next year? And we've got a couple of projects next year that are coming on. One of those, though, is purchasing, I think, 6 or 7 bioreactors, and we will be creating substrates and trying to evolve microbes and take the same approach from ones that are not as well known as rustacyanin. So back to square one, but with an awful lot of learning behind us. And we still think that even though there are far more readily available ways of doing in situ leaching that the industry are interested in and will pay for, that one day something like this might actually unlock that first block that takes us from A to B and creates no damage. Enzymes are wonderful things because they break down in nature into proteins and nothing. You use them when you use detergents. You use them when you do if you've got diabetes and you use those little blood swabs, those are enzymes that are on there that tell you if where your blood sugar is. So they are mass produced and they are used for things extracellular already. We just need to find the right one. In the meantime, have I still got a little bit more time, Rick? Oh, 5 minutes. Is that the full time? Okay, well, I might wrap it up there. I was going to talk a little bit about the tailings, but people might have questions on this one.
We'll hold the tailings in reserve in case there aren't any questions. But do we have any questions either in the room or online?
Yeah, he's going to make him bring it up. Please tell me you're not a protein chemist, because that would destroy me.
No, but I would like to tell you another time how exciting this is from for various reasons. But my question, sounds a bit contrived, but I promise I'll get there. When you mentioned about space and stuff, and I sometimes joke about the kind of alien anthropology committee as they cruise past Earth, and they're just like, so how are they doing down there these days, you know? And I can just imagine them sitting there, so one of them saying, oh, you know, they're doing that thing with where the bacteria get their metals from them out of the planet. They're only doing that now? Oh, God. Oh, well, that's good news. You know, good luck. So that's one picture I have in my head. And I do have another picture in my head, which is where they go, oh, they're doing that thing where the bacteria get the metals out of the planet. No, someone go down there and stop them. So is there any concern about the sort of second one, in the sense that as a very long-term strategy in 100 years or 200 or 300 years time, are people aware of concerns about this method?
That's a really good question. And I hope that you haven't copyrighted the two cartoons that I'm going to put underneath my two boxes, because they're fantastic. Look, I think when you look at just about any scientific advancement over the last 100 to 200 years, there are questions about the efficacy of those at the very start. And some of them are really reasonable and some of them are probably not. And the point is at the start, you don't know. And so I think for the ones that are saying, oh my God, don't look at that. I did mention that, you know, this stuff's in washing detergent and that it's in a number of applications now. So, well, it's new to us and it's not new to everybody in the room. I know some people are doing quite a bit of research in this specific area. There are already applications that are out there. So we're not splicing new life. What we're doing is taking protein strands and putting new things into them. They can't live on their own. And that's one of the problems with rustacine, the damn thing just falls apart once you take it outside. And you know, we need it to not fall apart. And I think also, especially in Australia, the you know, the hurdles that you need to go through for addressing ethical questions are pretty high. And the University of Queensland certainly has some pretty good policies on that, which all of our research would be passed through. Does that address your concern there?
That was a yes. Any other questions? Neil.
More exercise for Steve.
Can the next one come from up the back of the room again?
Thanks, Alice. That was fascinating. I guess one of the type of really attractive deposits for this technology are the deeper deposits where it's uneconomical to conventionally mine. But I guess at that depth, the environmental conditions can be quite harsh in terms of the temperature and the pressure. Is that something that can be investigated in a project like this? Can you replicate these temperature and pressure conditions?
You can if you're allowed to buy really expensive bioreactors, Rick.
Oh, sorry, I was talking to Steve. I missed that. Yeah.
Yes, you can, but you do need to be able to get bioreactors that you can replicate those print. And extremophiles exist, and they have been found quite deep in mines and also on the edges of, you know, vents around the Andes. And so extremophiles can be across the whole EH, pH, and temperature and pressure range. And so it's the enzymes that work in those that are of particular interest to us as well.
Okay, we've got a question online here, again from Alan Levitt, who I was almost sure wouldn't be able to resist asking a question on this topic, because I know it's dear to his heart. Thanks, Alice. Did you know there are as many microbes in the Earth's soils as there are in the deep terrestrial subsurface? They make a living, quote unquote, by interacting directly with the rocks and selectively extracting nutrients and metals. Have you considered partnering with teams to look in the deep earth for novel enzymes and or microbes?
Oh, that's a really good question. I've always been interested in Anthony Van Dert's work on how plants take up microbes, because I'm absolutely certain that the root soil interface, there are enzymes. In fact, I think I've read that somewhere, so it's not like my own novel idea or anything. The other thing that's interesting about that is that, and I won't take too long because I know I've just run out of time, the buzzer went, but that does lead directly into the tailings project that we're doing in conjunction with BRC and EAT Bernardino Vardas there, because it is the soil research and the ionic, the way that things that are in an ionic form move through soils and electrolysis that is now linked into this project. And we're thinking about basically sticking electrodes in tailings dams, pulsating and doing different coatings on them with Anita Parabar-Fox, and I think Mitch might be getting involved in that. And so the linkage of that, which isn't necessarily enzymes and proteins, has opened up whole new avenues, and that's come direct from soil science. So thank you for the question, and thank you, Rick, for the opportunity.
Thanks very much, Alice. That was great. So thanks. So we're going to move on now to the final talk for the morning, which will be it'll be a combination of Neil and Pascal. Is that the interactive online tools for communicating the geographic dimensions of complex ore bodies? So I'll put your presentation up. And one of you can, or are you going to switch back and forth here?
It's just going with one swap. So I'm just going to hold this here.
Okay, thank you very much, Rick. As Rick introduced earlier, we're going to talk a bit about water supply in the Atacama Desert. But really the theme of this is more on communication tools and the challenges and value of communication tools in the context of geographical dimensions of complex ore bodies. There's 4 of us on the project team. The other 3 are really the brains and the effort on the project. Pascal is going to help me with the second, more technical part of the presentation. Yeah. So the overall objective of the project is to start exploring the technical options for developing effective communication tools and tools that allow us to improve the dissemination of our research and improve the engagement of stakeholders in the research. And then specifically, our case study is about developing tools that can help education and stakeholder participation in our Atacama project. So we're going to focus on our case study later, but before that, just a bit about the broader potential applicability of such communication tools in the context of complex ore bodies. So the first illustration here on the left is an illustration from Eleanor's project that was talked about earlier. And there's many projects like this, not just in the mining context, but in lots of other contexts where maps of global risks are produced based on global data sets. And these maps are very powerful and can be influential, but underlying them are many layers of data from various different sources and of various different qualities, as Eleanor talked about. So one potential application of the kind of communication tools we're interested in is just allowing the user to really explore some of the data that underlies these maps, and also the sensitivity of the final map to the data layers that are actually selected and the weight given to the different layers. The other illustration here is from Mehdi's project on carbon accounting. And similarly, the type of tool we're talking about can be used, potentially be used by stakeholders to look at some of the sensitivities of carbon accounting to some of the geographical aspects of planning mines and mineral processing. For example, things like the location of the processing plant, location of the tailings plant, location of the port are things that can be played with and then looking at how that actually affects the final carbon account. Wrong button again. So geographical visualization tools we're all accustomed to. They're part of our daily lives now, and these range from very simple educational tools, cartoon-based tools, such as the one that SEG Water used to teach us all about their water grid in southeast Queensland. And then you get more sophisticated data mapping and data retrieval tools. So things like the Queensland Globe or Google Earth that we use all the time to explore geographical aspects of data of interest to us. And many of these databases now actually are interactive in the sense that you can actually access the underlying data from the map, such as the Bureau of Meteorology tools. And then at the far right there, there's tools like Google Maps, which are more powerful and are really interactive in terms of providing real-time information that allows us to optimize our day-to-day lives. What we're aiming at in this project, what we're going on to present in some more detail, is really focusing on the scenario analysis the most, and also some educational aspects. And our challenge is to try and produce tools that provide these functions but don't involve engaging a software company and spending 50% of our project budgets on developing these tools, but tools that we can develop in-house at relatively low cost, not top-level commercial standard tools, but nevertheless are effective for what we want in terms of disseminating our research and participating with our stakeholders. So the case study is under our smart water supply project that we're doing in the Atacama. So this is a 3-year project. It's been funded by the Mitsubishi Inversions Limited, which is a part of Mitsubishi. And this project has been running for a year. And actually our first complex ore bodies, which finished about a year ago, was very important in providing seed funding that allowed us to provide a very good scientific technical case for winning this funding. So we're very grateful for that previous funding. That's just a picture of the project team there. And the concept of this project is that there are water supply issues in the Atacama. In particular, water scarcity is preventing future development of mining projects. And there's also strong competition and issues with water around competition for water with traditional users. So what we're aiming at is to go from the present insufficient and uncoordinated water supplies to a much more integrated system where there's greater investment, in particular of seawater supplies, and greater sharing of water between all interested parties. So this is the type of outputs from the first year of this project, where we're just looking at scenarios of future demands for water, in particular from mining, and then looking at different scenarios of new supplies of water, and then trying to optimize efficient networks of water. So for example, the scenario on the right is the scenario where new mines are only allowed to use seawater, leaving traditional freshwater sources for everyone else. Now, what we don't want to do in this project is present results like this as a fait accompli or as somehow the correct solution. We need a participation process where we can sit down with the various stakeholders and allow them to play with our tools and actually explore the options and explore what difference it makes if you put more weight to financial costs or to environmental or to social impact. The tool we've got at the moment is not capable of doing that because it's quite a complex tool. We can set up scenarios, but it takes a few hours to set them up properly and to run them. So the challenge of this project is to develop a much more effective participatory tool that we can use in workshop settings. So the idea is to have a comprehensive tool, which we've largely developed already. And what we're working on this project is how we can simplify that. So at this stage, I'm going to pass over to Pascal.
Thank you, Neil. Yeah, on the right-hand side, you can see the current draft of the comprehensive tool. It's embedded in commercial GIS software, and towards the end of the project, the current idea is to reintegrate all the tools in there because we can write our own code and then provide modules that can be implemented in the GIS software. And a professional or someone who does planning at this scale will be able to use tools like that. But what we're going to focus on today is how do we come up with the left-hand panel that we see here. That's our prototype of the simplified tool that we want to use for stakeholder engagement. And I'm going to step you towards through the process a bit. It's not going to be so much around the technical part. For that, we have Martin in the room if there's questions about Python and integrating all that. It's really making the step from an environment like this, high resolution, 30-meter path network optimization, 12-hour for one processing run, coming towards a snappy interface that engages people and yeah, excites them. So the aims that we had for the simplified tool was
to educate. And what we got to keep in mind here, we're going to deal with an audience of variety of socioeconomic backgrounds. Might deal with school kids, university students, farmers, miners, mine planners, regional planners. So really have to simplify the underlying cost surfaces, which are currently very high resolution. And the first step was to reduce the spatial resolution, but very important to retain the character so that people who live in Atacama still realize, okay, this is the Atacama, this is my region. We want it to be interactive, barrier-free, and someone who uses it able to use it without any hardcore computer skills. Like if you can operate a browser, you can operate the tool. That was the goal, and hence we came up with the browser-based platform. And we wanted to be responsive and facilitate a good UI and UX. And for that, we needed to reduce the data volume significantly from our professional tool and pre-model everything to plug it into the browser. A big part in this, and you might have realized, this are hexagons. And me, Martin, and Liana had one meeting where this idea originated. And I think the seed was a German board game, which is an international success, big one, Settlers of Catan, where they utilize a hexagon map. And hexagon maps it's not a new thing. You see a map here from 1895, a city planner for London actually employed this concept to separate London into different zones. Since the 90s, roughly, it's used in video games as well a lot, particularly war games, where the movement from one hexagon to the other is a critical part. And this is where actually big advantage lies over the classical square grid space. If you step diagonally in a square grid space, you have a different distance that you're covering as opposed to the neighboring cells. For a hexagon grid, it's always the same distance. So it makes our life, Martin's life with the coding a little bit easier, because every connection that we want to model for a potential water pipeline is the same. For me, the main thing, and I think for us, how we came up with this was also the nice appearance. It has a very organic appearance to it, a hexagon grid, due to softer edges, and it's visually attractive somehow. I don't know what it is, but you read that everywhere where you read about hexagon grids. So the underlying cost surfaces where we model our potential water pipeline connections over in the comprehensive tool, the professional tool, is based on a 30-meter resolution grid utilizing topography, environmental costs, and a combination of those to then model path networks that are optimized for this combined raster underneath. So currently looking at 40 to 50,000 connections that we're modeling in one path. Way too much for a engagement tool. So what we then came up with was resampling the cost surface. And I think it's amazing how the character of the region is retained, and even the character of the underlying cost surfaces is still coming across. You can still see hotspots, environmental valuable zones, and then the combination as well. And on the right-hand side, you see our simplified path network, which is simply the connection between all the hex centers. Next up, I've prepared a little video, a little demonstration of the current browser-based prototype, just to look at the interface. We have on the left-hand side, we have the map interface showing the underlying cost surfaces. In the beginning of the demonstration, you will see we're using the slider on the bottom to toggle from left to right to illustrate the different aspects. And what we're going to see in there are lines connecting different hexagons, which are pre-modeled, and the optimal path connections based on the combined costs between different hexagon cells. We're going to see in the right-hand graph the elevation gain over distance for each of those paths, and then the relative path cost and how they accumulate. And I'm just going to, hopefully I can play it. Oh, hang on. Yep. So we're sliding left and right, combined cost, and then connecting the different grid cells. And that's currently just for one data set. We have 200 more of those where every grid cell can, hexagon cell can serve as a starting point and connects to all the others. And to conclude, currently have a functioning prototype created, which is a good platform for future extensions to make this a more educational tool, for example. Highlight, okay, where are the benefits of using shared water infrastructure? In this tool, you can brilliantly do it. Just have the user select maybe 5 connections in between, and then yeah, show how much money you saved because you're sharing water infrastructure. The tool has been used actually this week, I think twice already this week in conference workshops, and next year we'll really start to engage with the stakeholders in Chile and have them use it and wait for their input. There's potential value here of the methods and skills to other projects in the Complex Orebodies program in terms of the platform that we're developing, but also the resampling approach. I think stepping back from your science, dragging yourself out of your rabbit hole and really going 5 steps back and sit together with people and talk to it can lead to some great outcomes and then really be beneficial for your science communication. Thank you.
Got lots of time. Do we have any questions either online or in the room for Neil and Pascal? We've got one from Marcy. You might have to relinquish yours. You guys can maybe share the lapel one back and forth.
I'm Marcin Zemski from SMI Production Centers. Really enjoyed it. Elegant solution, and I was going to say simple, beautifully simple, but it's elegant, and that's great. Have you looked or had any interest yet in applying it to other flows? I work in energy, so I was thinking electricity. Is that something that you've explored or have had any interest in so far?
I haven't explored it, but certainly a interesting idea for Queensland and the challenges ahead that we just heard about today. We've been looking in another project completely unrelated in the potential of reusing high voltage power lines in Queensland for renewable energy projects. Yeah, what's also powerful about this hexagon world is you are able to, well, as you're lowering your resolution a bit, you're able to consider connections that are not there yet, without having a massive overload of data and computing. You're just making a rough regional model. And we are experiencing this in the Atacama as well. We have regions that are currently not equipped with the source node or a destination node, but the hexagon world actually does allow us to consider it at least as a hub for potential reservoirs.
Yeah, I'll just add to that. It was in this project, it was never our intention to apply the tools to also map out the electricity supply. However, that has been raised as a significant issue. And if you map out the existing seawater supply projects, interestingly, the power supplies don't follow the pipes, not always. And so it's not the same supply grid. So there definitely is something to look at there.
Thank you. Really, it was very informative and interesting presentation. Just wondering about when you talked about this environmental and economic costs. So what sort of the data you captured, the economic cost, the environmental cost, what are the unit of measurement like that?
That's a good question. So the economic cost, well, it's just generalization about the capital and operational costs of water supplies. So the costs of desalination plants, the energy costs for pumping the water. So there's a lot of data on that from around the globe now, lots of studies about the costs of that and how the costs are changing. It's very sensitive to energy costs, which is difficult because our projections of energy costs even 2 years ago when we were developing this proposal are not the same as what they are at the moment. So that's quite interesting. The environmental costs, we've got a PhD, Claudia Moreno, her PhD is about what are the environmental costs of these schemes and how do you develop metrics of the costs. At the moment, we're just using essentially maps which show environmentally protected areas, areas of special ecological value, etc., both terrestrial and offshore as well. And then we're just attaching penalty costs for the number of pixels within these areas that the pipelines are transversing.
Oh, thanks. Yes. So you mentioned the economic and the environmental costs there. Do you tie the, I guess the pros, I'm thinking of the social costs, but also the benefits as well. Are they somehow tied in? For example, if you're looking at your pathway route and it passes a town that might be able to benefit from that, etc. How is that tied in?
So the benefits we've not looked at yet. I mean, the benefits are essentially posed as constraints. Like if a scenario is there's a new mine here, it needs a certain amount of water. So that's a constraint that we have to meet. We have got a new PhD starting on January. One of our students has been stuck around for the last 2 years trying to start, but his PhD is going to be about the benefits, in particular, the benefits to agricultural development. But our effort so far has just been on the costs. The social costs are in this area are largely tied to the environmental costs, things like concerns over brine discharge from the desal plants, noise from the pumping stations, and just the visual impact on the environment.
Maybe to add on to this, regional communities and farmers are considered as supply nodes in this model. So for some of them, for the first time, we put them onto the map for water supply system. Yeah.
Actually, it's one of the importance of this tool we're developing, in that we've had to make some pretty strong generalizations in our cost functions, right? But when we actually show our results to stakeholders, they'll be able to provide us feedback on whether our generalizations are acceptable, whether they're working for their particular concerns.
Lots of questions. I've got one at the back here.
Interesting presentation. I have a question. So when you take seawater supply into consideration, what are the challenges in the modeling?
Yes, that's a good question. The main challenge from the point of view of the buyers of the water, so that's mainly mine companies, is just the cost of treating and pumping the water over large distances. So the largest seawater supply is for the Escondida mine, and they paid $3 billion just for a supplemental pipeline. So that gives you the scale of the costs involved for the companies. So there's many new mines which are higher up in the Andes, or mine projects, which have not been confirmed yet, simply because of the water supply challenges. The environmental issues with seawater supply so far has been primarily concerns over the brine discharge into the ocean and the cumulative impact once you start getting 5 or 10 desalination plants in the same region.
Any others?
I had a question. Hopefully this mic's working. It's really, I mean, it's really super interesting stuff, but I've been sort of trying to get straight in my head what benefit the sponsor sees from this project. What are they? Why? I mean, I don't want to say why are they sponsoring this project? Oh my God, I can't believe it. It's more like what's the main benefit they are deriving from this work?
Well, the work's funded by Mitsubishi Inversions Limited, which in my understanding is Mitsubishi's foundation, which supports public good projects. So they have interests in mines in this region, and their mines are either short of water or are investing in seawater supplies. And there's obvious public concerns about the shared benefits, public benefits of these new seawater supplies. And so really that's what we're investigating and trying to communicate and explore how the shared benefits could be better.
I didn't mean to interrupt, Rick. Yeah, I had two comments. I think when you begin to gamify something, it just generates lots of excitement and ideas, and you can tell that just from the questions in the audience and the possibilities we all see here. And so there've been questions around the energy, and I guess one comment would be, is there a potential to build forecasting into this tool? So in the future, if you do begin to look at energy pipelines and so on, could stakeholders then ask themselves, what happens if I build in renewable solutions into my project and to the results?
Well, we can do that in terms of altering the cost functions, I guess. You know, if the cost of energy supply changes, then we can see what difference that makes to the optimal flows of water. I mean, if you want to go deeply into, you know, what are the actual real costs of renewable energies versus traditional sources of energies, that's something, you know, we'd need some help with, because that would be difficult for our project team to go into that. But if it's simply them saying, here's the cost of this supply, here's the cost of this supply, we can do that. It would be terrific if we could have an energy, you know, an electricity supply component to this project, looking at questions like, you know, with these big pipelines, they need 3 or 4 pumping stations along the length of the pipeline, right? So there's a question of whether these pumping stations should have their own localized energy solar farm, right? Because most of these are, or the new ones anyway, are being provided for by solar energy. So should the pumping stations have their own solar farm, or should there be a centralized solar farm then with transmission lines? That would be really interesting to look at, but that's not part of the proposal at the moment.
It sounds to me like there's a collaboration with Marcin here in the room, and also with in the ISAP project you'll hear in later on. We've been collaborating with Ali Madasey from UBC, whose expertise would be able to help with that. Sorry, Rick, over to you.
Okay, well, I was just going to say you finished way ahead of time, and we used all the time with really good questions, which is, I think, the best outcome possible for a talk. And I only just wanted to have a couple of final comments. One was that, as somebody who has a misspent youth as a war gamer, I'm very used to hexagonal boards, and I think they're a great idea. And then the other thing is, I used to play a game called Rail Baron, and I could just see a game called Water Baron here, and I think you should really try to fully gamify this, and not just sort of gamify it enough to be something that you can sort of sell to your stakeholders. But anyway, it's lunchtime, so it was a great way to finish the morning. I'd like everyone to thank Neil and Pascal, but all the speakers from the morning. And then we'll be back.
Thanks very much, everyone. We're going to get back going again. And we'll start. I hope everyone had a good lunch. And I know we lost a few people online. Maybe, hopefully, some will filter back in. We're going to start this afternoon with a presentation, a triple barrel presentation from Lisa, Christian, and Marcin on low footprint processing. So all yours, Lisa. Thank you very much.
Thank you, Rick. Can everybody hear? Hopefully everyone can hear me online. So thank you very much for coming. As I said, I would like to first acknowledge quite a few people who have all contributed to various aspects of this work. There's Christian, Antonio, and Marcin Zemski, who are going to be out here presenting their bits of the work, but also I'd like to acknowledge the contributions of both Frank Shi and Kim Runge, who have been very integral to all of the work that is going to get presented today. well, the concepts of the work that the work addresses. So there has been a lot being said about the necessity to reduce the footprint of mineral processing operation. But why do we even worry about footprints? Well, these are statements that I'm sure many of you have heard over and over and over again, and that is because they are remarkably salient points that simply need restating every time we talk about something like this, and that the need for minerals is escalating because the amount of minerals that we need to process and the amount of metal that we need to produce is simply escalating at an exponential rate. During today's panel, we heard some fantastic numbers being rattled off at us about just how much more metal will be required to produce an electric car. And electric cars is what we need to do to get away from fossil fuel-based economies, which is becoming rapidly critical to curbing the harmful effects of climate change. But to produce the sheer quantity of metal, we need to process more ores. And as you also keep hearing over and over again, the grade of ore deposits is decreasing at a tremendous rate. So to produce the same amount of metal, we're now having to treat order of magnitudes more ore than we did 20 or 30 years ago. And so the mining operation continues to scale up and up and up to be able to accommodate the enormous throughput that is required to achieve the amount of metal that we need to produce. And that amount of metal demand is simply going to keep going up. So to give you an example, this is a Google Earth image of what at some point probably still is world's biggest man-made hole in the earth, and that is the mining operation at Chuquicamata. I cannot testify to this firsthand, but people who like to brag about the sheer size of their hole compared to other people's hole claim that this particular hole is visible from space without the use of a telescope. Again, I cannot confirm or deny since I have not been to space. So again, what does that mean in numbers? It means that the amount of metal production, copper production in particular, where is the pointery thingy? There it is. Yeah, okay, there it goes. We have an exponential increase in the demand of copper. So by 2050, and 2050 is 27 years from now, it is not that long, we will be requiring 45 megatons of copper being produced. Consequently, we have the exact opposite trend. We have the steep decline in the grades of the ore bodies. So as a result, we are treating truly stupendous quantities of ore material in order to meet demand. And how do we normally do that? What does a mineral processing operation look like? Well, the design of a typical mineral processing operation has not changed in approximately 100 years. And it goes something like this. You have a mine, you mine your material. Where's my pointer? Pointer. Okay, you mine your material, it goes through a crushing station, a section to reduce the size, which requires a lot of energy. You then go through a milling section to reduce the size some more, which requires even more energy. You then put it through a classification section, which thankfully requires a little bit less energy, and then you put it through a processing option, either flotation or gravity separation, which don't require all that much energy, but take up an awful lot of space. And from that, what we have left over goes to a waste dump. And those waste dumps, as I'm sure you know, because a lot has been said about this, not only do they take up an awful lot of space, they can be unstable, and they can fail in a truly catastrophic manner, killing hundreds of people at a time, as we have seen over and over again, repeating story over the last few years. So this is something that simply cannot be sustained. This picture has to change in order for us to be able to continue with our society and then meeting the demands of the metal that society requires. So this picture is no longer viable. We need to change it. How do we do that? And so what are the major footprints that we need to worry about? I've already mentioned the energy footprint. A mining operation takes up the energy of a small city. When I say small city, I mean Brisbane. And so comminution energy, in other words, those first two crushing and grinding sections, take up 40% of the energy demand. So think about the city the size of Brisbane. Half of the day that is spent powering that city is also spent on crushing rocks. So for base metals alone, that accounts to 0.4% of total global energy use. Okay, that is significant. And all of that is information that I'm sure you have also heard many times before. It's been very well detailed and very well published. None of this is new. And once again, we go back to Tricky Kamara, which is very proud of how big it is. And over here, we have a image of, I took this picture in 2013. And at the time of taking that picture, this was the world's biggest SAG mill. I'm not sure if it still is, but it was in 2013. Also, the people there kept telling me with much pride. But just to appreciate how big this thing is, see, that is a guardrail. So a person would be roughly this high, and the rest of it is pure mill. So that's energy. So that is a comminution section. What happens with flotation? Flotation does not take up that much energy, but it takes up an awful lot of space. So the size of flotation cells has also been increasing exponentially. We have gone from, hold on a second, this is the wrong order of the pictures. We have gone from the early 20th century, where the average cell was 1 to 2 cubic meters in size. By the 70s and the 80s, we were looking at approximately 30 to 40 cubic meters. And now the average cell being installed is approximately around 600 cubic meters, with some 800 cubic meters installations that are not unheard of. We've gone from something like this to something like that. How much more can we keep increasing the size of flotation cells before everything starts falling over? The answer is we can't. So what we have to do is we have to change the way that we do our processing. And the two technologies that I wanted to highlight today are those that are being quite extensively looked at here at the JKMRC and the BRC. It's sponsored by the Complex Orebodies Program. Is we can reduce the amount of material that we send to comminution, thus reducing the amount of energy that we spend by making use of this really exciting new technique called higher voltage pulse comminution. And Christian is going to come up here very shortly to talk about that. Another is that we need to get smarter about how we float. And we do that by treating coarser particles that require less energy to grind them. And we're going to do that through looking at coarse particle flotation. And we will go into a bit more detail on each one of those techniques. And we will sum up with Marcin talking to us about the energy implications of doing both of those things. So Christian is up next, and he will talk to us about HVP technologies.
Thanks, Lisa. Second part of the speed dating, speed presentations. So I'm here to just give a brief background on high voltage pulse combination and at the JKMRC, the work that has currently been done and the advantages of this with respects to what Lisa were talked about. So what is high voltage pulse technology? So high voltage pulse technology isn't a new concept. It's the use of electrical energy to break rocks. It uses short pulse energy at very high speed and transfers this energy to basically through a solid, which creates a plasma, which then creates breakage through a piece of rock. It's not a new concept. It's been around since the 1970s in ore comminution, but it hasn't really taken off because of the high energies that was required during that time. At that time, energies of around 100 kilowatt hour per ton was being required to break to break rocks and improve the liberation. So HVP technology research started at the JK about 2007. Started here by Professor Frank Shi, who shifted the use of HVP from being a comminution device to a pre-treatment method. So by doing this, we reduced the energy requirements for HVP significantly from 100 kilowatt hour, which is unpalatable to mining companies, down to less than 10 kilowatt hour per ton, while still really getting the benefits of the HVP itself. So at the JKMRC, we've got 2 HVP facilities. We've got a batch self-frag lab unit that we do most of our experiments on, and a newer flexible HVP facility, which we're using to scale this process up from batch scale to a semi-continuous scale. So the work that Frank and the earlier researchers has done has really made an impact on the technology, reducing that initial energy consumption from 100 down to less than 10. And this work has really made a big impact. And as a result, they won the SEEK 2017 medal for this technology and for their work. And it's been dubbed as a potential game changer technology for the industry. So how does HVP work? So if we consider an electrical circuit on the right here, stored energy is stored in capacitors, and this is released through a series of electrodes. And from this positive electrode, a plasma stream is generated to a bottom electrode, which then goes through a solid. If the release of energy is high enough, this plasma stream, or this energy, a bolt of lightning basically, passes through the solid instead of the water. So everything happens here through in processed water. So when the energy is released, a plasma stream is generated, and this plasma stream has a tendency to, I guess, search out the most conductive pathways through the top electrode to the bottom electrode. And so if we had particles, mineralized particles in between these electrodes, the preferential path is to go through these conductive minerals and then breaking these particles up. So it basically selectively searches out the mineralized particles and breaks these and leaves the barren particles alone. So if we if we consider 2 mineralized particles, these are two synthetic ores. The one on the left with the O is a mineralized particles with an embedded chalcopyrite grain, and the one on the right is basically a barren particle. So once the pulse is released, the product selectively destroys the particle with the mineralized particles, breaking it and causing micro cracks and exposing the mineral itself. The barren particle itself is left untouched. So I don't have time to show a selective breakage video, but I've left the link there for those who are interested. It shows the cell frag being used on both synthetic and also real particles, so which is will be good to look at. So like I said, at the JK, we're not focusing on using HVP as a comminution device. We're using it mainly to pre-treat material and get the benefits of the high voltage pulse. So we're using it to improve ore processability. So if we do have ore particles and which goes through a HVP process, we can, after the breakage, we can do a pretty much a screening process whereby we get the broken particles, which is high grade, which means that it's been pre-concentrated, and the barren particles, which are low grade and the ones that haven't been broken by the HVP process. And we can screen these and get two streams: the low grade particles, which can be rejected or processed through a different way, and the high grade stream, which can go through the process. In doing it this way, we've already rejected a large portion of material which is barren, so we're not wasting energy in the downstream processes comminuting these. So if you consider, if you look at the graph on the right here, this is pre-concentration curves of a gold ore that's been through HVP and normal mechanical breakage. And you can see here, HVP can achieve pretty much a 70–75% recovery of your gold material in 50% of your mass. So that means that you can throw away 50% of the mass and only lose 25% of your gold. So the other benefits of HVP is that this high grade pre-concentrated material that's been already pre-broken also has received a lot of microcracks. So it's pre-weakened already. And if it goes through the comminution circuit, the energy required would be a bit less. It also has an added advantage of better mineral liberation because it targets the highly conductive material in the particles. The plasma streams or the lightning actually go through them and break at the surfaces, so exposing more surfaces for downstream recovery. And again, like I said, all these benefits can be had with very 5 to 10 kilowatt hour per ton, which is more palatable to the mining industry. So if we wanted to implement this in a mining circuit, I think it's best to put it up front where we can get all the benefits of pre-concentration, coarse gangue rejection, and the pre-weakening of the material before it goes through the mineral circuit itself. We can then use other technologies to recover the highly exposed minerals or the improved liberation through different technologies that like hydrofloat, which Lisa will now.
Thanks, Christian. So now that we've spoken about high voltage pulse comminution, we can talk about the second half, and that is coarse particle flotation, which is a technology that has been identified as one of the foremost areas where significant improvements are possible in mineral processing. So what we need to do is we need to change the way that we float minerals in a way that is not constrained by the coarse size of the particles. And I will not go into too much details about how that works because we're kind of running low on time. But it is a radical departure from the standard way in which we do float tests, where in a traditional flotation cell, we have quite a high degree of agitation with a high energy input, where coarse particles simply cannot hang on to bubbles and become pulled away from them from shear forces. So what fluidized bed flotation does, it creates a coarse particle friendly environment where the particles in the bubbles are brought together in a very gentle yet concentrated environment that allows them to have enough of time to stick together and stay stuck as they become recovered over the size of the cell. Again, this technology is also by no means new. It is commercially available, and as of the last couple of years has been installed in several mining operations at full scale. And the two main technologies that are available are the HydroFloat produced by Areas, which is already available on the market, and the NovaCell developed by the University of Newcastle, which has recently been bought out by George and is in the process of being developed for commercial dissemination. And so this graph here shows a very strong advantage of what can happen when you have a coarse particle that contains quite a lot of valuable mineral, but has a very, very low degree of surface exposure. And it is these areas of surface exposure that get stuck to the bubbles. And because there's so few of them and the particle is so big and heavy, it's very important to make sure that we do not apply any force to try and tear them apart. And as a result, you can have a recovery of pretty poorly liberated particles at a significantly higher rate than you can using conventional flotation cells. And as a result, here you can see in black, we have a standard flotation operation, which drops off in recovery dramatically as soon as your particle size reaches 100 micron. And you have gravity separation processes, which I've showed you on the flow sheet earlier, which only picks up in efficiency once you get to about a 200 micron range. Yet the HydroFloat, in this particular case, fills up the gap between the two, allowing for the recovery of the particles in that particularly troublesome range. And so here is, come on, mouse. Here is the very first full-scale installation of the HydroFloat at the Cadia site for Newcrest, pictured here alongside with Luke Follett and Bridget Seaman, who were the team responsible for bringing this project to fruition. And as you can see, there it is, big and proud, a brand new step change installation in the mineral processing operations. But what does that actually look like in real terms in terms of saving energy? What you could do is when you've got your high voltage pulse comminution device that is already reducing the amount of material that is being fed to the fine milling operation, you can also place your coarse particle flotation device directly in front of milling, where you are now further rejecting coarse gangue material, further reducing the requirement for putting all that material through this extremely energy dense milling circuit. Not only are you doing that, you are sending far less material through your flotation circuit, thus no longer requiring the need to have gargantuan sized flotation cells. And all of that coarse waste is being bypassing both the milling and flotation devices and going straight into your coarse waste stream. And so we have significantly reduced milling energy and a significantly reduced flotation footprint. And to talk about what that actually means for real quantities of energy savings, I'm going to hand over to Martin, who will talk us through the energy implications.
Thanks, Lisa. Just jump ahead, yeah. Great, so energy implications and just general implications besides energy by themselves. So this is one of the earlier flow sheets that Lisa shared with you at the beginning of this session. And as you can see, I've added some potential flows there, some potential streams. And we're looking at a pretty standard flow where you say about 1,000 tons an hour is pretty typical of many operations. Some are larger, some are smaller. And in a typical operation, that 1,000 tons an hour goes through the whole process. It goes through the process of crushing and grinding, and it goes through the process of flotation. So we're essentially pushing the whole 1,000 tons an hour through every part of the process. And of course, that ends up with whatever mass pull we have in the final concentration, in this case, flotation. It might be 10%. So 100 tons an hour goes to flotation product, and the other 90%, 900 tons an hour, goes to tails. Nothing crazy about that. Now, what happens when we start introducing these technologies that we've talked about, the high voltage pulse and the coarse particle flotation?
Well, currently those technologies, in particular coarse particle flotation, is being tested. It is out there in full scale, but it's been tested in different parts of the circuit that are fairly low risk as we learn more about it. The high voltage pulse is also in the test phase. Perhaps it's not yet out in the field, but we're certainly looking at already having continuous prototypes in operation. So if we start introducing them, like Lisa, oh, I'm going the wrong way. Like Lisa suggested, that we have a circuit that looks like this, where we have high voltage pulse early on in the process, followed by coarse particle flotation. Well, if we stick to our 1,000 tons an hour feed, we all of a sudden say, okay, well, let's reject that 30% that Christian mentioned in high voltage pulse, and all of a sudden we've only got 700 tons an hour going through the next part of the process. So we've already removed about 30% of the material from the process going to waste. It might not be waste, it might be leach, but at least it's not going through the bulk of the plant. Then if we introduce the coarse particle flotation, as Lisa indicated, then we might be rejecting another bunch of material into waste or some other processing, but we're not sending a huge amount of material into our final mill and our final separation and flotation. So you can see here that in my example, we're only sending 100 tons an hour into the mill. That's 1/10 the material of the original circuit. And so we're only doing the final processing and final separation on 100 tons an hour. And our final tails, which is the fine tails, is no longer 900 tons an hour, but now it's only 70. Now, this is one example. It could be many, many different options that this looks like. But as we see that there's a massive difference in, of course, what that might mean, you might say, well, my milling circuit's already there and it's designed to handle 1,000 tons an hour, or my flotation circuit's already there. I've got sunk cost. It can handle 1,000 tons an hour. How do I capture these technologies and use them? Well, perhaps you can put 5,000 or 6,000 tons an hour through your crushing circuit and through your HVP, if you can get a HVP capability to run that amount of material. And of course, then you can remove your waste and still end up with a fair amount of material going into your mill and using that mill to its full capacity or close to its full capacity. So the again, going back the wrong way. There we go. So I'm just highlighting those for you, the pulsing. But really, what does that mean? Well, the throughput, it might be the same or so, but as I said, you might end up putting a lot more material into the front of the circuit and perhaps increasing the throughput by up to perhaps 10 times. It depends on your capacities of the different units. The fine grind is perhaps 1/10, it might be 1/8, might be 1/12, but it's significantly different, significantly reduced amount of fine grind. Fine tails also is much smaller. In particular, the main point of the discussion here is that the energy used overall is likely to be about half. And I haven't gone through all the details, but of course, there's a lot less energy used in the milling and flotation, obviously, because you've got a lot less material going through those parts of the circuit. But of course, you will use energy in coarse particle flotation, and you'll certainly use energy in a high voltage pulse. But overall, you're looking at about half the energy. That's not taking into account the softening and the micro cracks that are introduced in the high voltage pulse. So that half is probably going to go down even further when you take into account that it's much easier to break material that's gone through a HVP. Yeah, finished. That's it.
I'm going to try to talk about a couple of things in this talk. And what I will say is that the reason I wanted to talk about future opportunities is that we're very much at the stage where we're coming to the end of the 4th year of a 5-year program. And we've been talking back and forth for a while about what the plan is in terms of, in terms of a continuation of the Complex Orebodies Program. The Complex Orebodies Program will continue past the end of next year because we have a whole series of multi-year projects that are continuing past the end of next year. But I think there's been an enormous benefit to having funds available to do seed projects, to provide seed funds for projects that provide proof of concept that then lead to relatively large amounts of industry funding. And there were a few that were mentioned today. Or let's not talk about it in terms of funding, to lead to much more ambitious and potentially impactful projects. So, but what I want to do first, and the other thing I want to do is talk a little bit about some of the other projects as well that we haven't talked about today, because we've intentionally spotlighted a few projects, but there are other projects that are very significant that haven't really received a mention. So I'm going to mention them just because they're still very, very important projects for us, and well worth and really deserve a mention. But before I do that, what I wanted to do was talk about something that we've been working on for the last little while, and to some of you it may be very obvious, but the background here is that we're working on, as Eleanor mentioned, there's a special issue that we're working on complex ore bodies, where we're producing our own contributions, but also have solicited contributions from other people who are talking on the theme of some of the topics we've dealt with today, which is really thinking about things other than the pure technical risks associated with projects. And Eleanor and I, and Deanna and John, a few others as well, we're working on the introduction to a sort of overview paper for that. And I spent a lot of time thinking about whether, how we should think about projects. And I'm a bit worried that people do this anyway, but I just wanted to talk about, I guess, the change in thinking I've had about projects from 4 years ago to now. So I come from an exploration background. So this is kind of this. I spent sort of probably 20 something years pursuing this graph, timeline of going out, spending a relatively small amount of money, identifying an area that you think has an ore deposit in it, finding that ore deposit, having the value of your company and shares increase enormously, making a discovery, then going through the feasibility period where everyone gets bored with that discovery, and if it's good enough, then it becomes an operating mine. And as you can see, that's a sort of a very linear timeline, and no project follows that exactly, but it's the sort of thinking that pervades the exploration and mining industry. I think when people think about their projects, that's what they think about. And Ed's not here anymore, he's left, but I borrowed this from his presentation at the Deep Mining Geology course, and it was looking at a mine planning process from strategic planning, tactical planning point of view, looking at different scenarios, developing a whole series of processes that feed toward hopefully a positive outcome. And I think everybody in the mining space is very comfortable dealing with this sort of picture. And I think what that leads to is that when we're thinking about the social and environmental aspects of a project, we incorporate those social and environmental aspects into that thinking. So we either, on the left there, we're taking that project and we're slotting it into what we perceive to be the environment that project lies in. And it's just a pretty easy thing. You just stick it into the pre-fitted the pre-fitted space, and you're away. Or that we think of it as one in a series of hurdles to go from the first concept of the project to an operating project. You just jump over all these hurdles, and as long as you get them all dealt with, then you're fine. But and I borrowed this from is that going to work? Is that going to play? It's not playing. Have I got to hit? Yeah, there we go. So I borrowed this from Malcolm. And I don't know why his name isn't appearing there. So we've found an ore deposit. We put a pit in. We built a mill. We put in some infrastructure. We've got some waste dumps, and then there's a drainage. And so we built a tailings dam in a place that makes sense, and we need power. So we built a power plant, and we built power lines that go across the countryside next to the town. We've got some trucks going back and forth. This is all borrowed very heavily from Malcolm's presentation. We got a field of water bores over there in that area over to the east. But of course, that means we've got a lot of dust from all the trucks, and we've got contamination potentially associated with the waste dumps, and contamination and or spillage associated with the mining or the tailings, and balancing, and we've got noise, and balancing against that, we've got monetary benefits, and we've got potential improvements in quality of life, and of course employment. We also have the danger that the mining, or that the community near that mine doesn't see any of the details of the mine. All they see is the effects of the mine, which is noise, dust, and contamination. So it's I guess what I'm trying to demonstrate here is that a mine is and you know, I'm not telling you guys anything you don't know, that a mine in itself is a very complex system, and a mining project is a very complex system. And what we're doing isn't jumping through a series of hurdles in a isolated environment. What we're doing actually is taking the very complex system of a mine and attaching it connection by connection. So this is from a paper on an urbanization, a model of dynamic model of urbanization in China. And all these connections are different factors that are feeding back against each other. And what a mine development is the process of taking this complex system and plugging it in to a whole series of these connections in various different complex ways. And so what that means is that we're nowhere near the idea of a simple jumping over a hurdle and getting the social, economic, environmental things done. We're in the process of grafting a mining project onto a very complex system that will have ongoing and complex effects that will be feeding back against each other. And so I guess that when you think about a mining project in that sort of context, and the reason I'm talking about this is that it leads to a whole series of things that you have to think about that we don't understand. They're the bits that we're working on already, and we've heard about today, like how to reduce the footprint of the mine infrastructure, or the plant, or the power, or any of those sorts of things. So that's something that we are addressing, but we could do a much better job at. And the other thing that is a growing challenge that we're also becoming increasingly involved in is how can we produce the same amount of metal from this mine while using much less power, water, and other things that have an impact on the community. And of course, we're doing a lot of work, as I'll talk about in a second, on minimizing or eliminating tailings and waste from that mine. And how can we reduce contamination, risk, volume of tailings and mine waste, and maximize its value and reuse. So those are topics that we're addressing, but there's an enormous potential to do more on that. And even more importantly, in fact, I think most importantly, is how do we actually understand every one of the important connections between these two complex systems? So this is not a system where there's a pipe going between the mining project and the community. There are hundreds of connections. And in order to understand all those connections, we actually have to do complex multidisciplinary study of the type that we talked about today. And that's the point that we're trying to get off, or get out in this paper, that it's that we're talking about a whole series of connections, not just a single one. And what are the important connections? How do we determine that, and how do they interact? And so I think that that's really, if I was going to identify one priority of ongoing work in the Complex Orebodies project, it would be along this theme. What are the important connections between the complex mining project and the complex environment into which it's being grafted? And how do we get better at understanding those connections and then taking those lessons and feeding them back to industry in a way that it can operate, taking into account the optimal outcomes that they could strive for in that sort of setting. So, and of course, what that is also connected to is how do we place a value on all of these factors? So we're plugging into all these things in a complex system outside the mine gate, and they're having an effect on those. And the mine itself is having an effect on all those factors, either positive or negative. And how do we place a value on that, and then translate that value into project planning and optimization that will allow us to optimize the connections between those two complex systems. So I don't have any answers on exactly what we're going to do, but I guess what I tried to demonstrate is the lessons I've learned over the last 4 years about how I think about a mine now in comparison to how I thought about it, when this thing started. So people have talked about this already, so I won't spend too much time talking about it. These are all the themes that we've dealt with, or that we're dealing with as part of the Complex Orebodies program, and we've touched on a lot of them today. I do want to give a little bit of an update, and some of you will have seen this very recently, so my apologies to you over that. So we started in 2018 with $5 million strategic funding. We've got 1 year left to go. We've had a large number of UQ researchers participating, and we're now up to over $15 million total if you include the UQ funding and external funding. Large number of projects with a high degree of cross collaboration within the SMI and outside the SMI as well. A large number of external partners, a growing number of publications, and we continue to have a large number of those in review. We've sponsored a lot of students and postdoctoral research fellows. I won't go through the rest. I've covered most things there. One thing I did want to get onto, so that graph up in the upper right hand side, basically the target funding for the whole project is shown in orange, and the actual funding that we're going to achieve from industry sponsors is shown in blue. What I've tried to do, without putting budget numbers down and all that sort of thing, is just look at where that external funding is coming. You can see that the community and social performance and waste characterization are two of the biggest areas of, not surprisingly, of focus for the industry. Number of case studies, strong support for water research, looking at variability, prediction, visualization. So really support across a range of the topics that we've identified as being important. But what I did want to touch on briefly was some of the things we didn't talk about today. I already mentioned that, but really probably, from the start, one of the most important areas that we've been focusing on, and one of the areas where I think we have the greatest chance to have an impact if we, if we continue along the path that we're going, which I think is a good one, is in transforming community and social performance. So developing the understanding of all the different facets, some of which Anthony touched on, and Eleanor early on, but all of those complex aspects of the interface between the outside of the mine and the inside of the mine, that where the potential impact is changes in the way companies view the situation in a way that allows them to gain access to ore bodies that they wouldn't have otherwise gained access to. As I showed, our biggest project in terms of external support is removing contamination from the mining value chain, looking at mine waste and opportunities, characterization, and so on from that. So we've seen that in previous versions of this, and so I'm not going to spend a lot of time talking about it other than to say this is a very important aspect of the work that we're doing here, and a very important aspect of I guess, moving to a situation where we can, unlock some complex ore bodies. Another highlight for this year, I guess, was, and this is earlier on in the sort of exploration, discovery, construction, mining continuum but it's under the variability prediction visualization theme, is a large project that's commenced with the Queensland government on building a digital Earth visualization of Queensland, which we hope to expand to a much greater area that has a great potential to synthesize data sets that cover the whole range of activities we do, from social to environmental to geoscientific, that started this year. We're continuing to do important work on the variability and flexibility side of things from a mineral processing point of view, where the aim here is to pursue these sorts of faster and more flexible approaches as a substitute for bigger and bigger everything. So, I've shown these a few times. The blue in the background are really the strategic goals, if you like, or the sort of the vision of different areas where that we'd like to ultimately arrive at, but we're not going to arrive at the end of the 5 years of the Complex Orebody Program. And I guess placed adjacent to them some of the aims of the program itself. And of course the other thing, and I've ended talks like this a few times with this sort of picture, and that is that there's a whole group of people working across the SMI and UQ more broadly and outside it that have contributed to this, and that's been part of the aim of the Complex Orebodies Program as well. So we're continuing to work. We have a lot going on next year. We have a large amount of projects continuing, and we'll be going through the process over the next little while of I guess making a pitch for a continuation of the Complex Orebodies project with support in addition to project-related support. So that's probably all I wanted to say on that, and I think that probably just about gets us back on schedule, because I was 10 minutes faster than I thought it would be. So, but before we leave that talk, is there any sort of questions or comments anyone wants to make at the end of nearly at the end of a very long day? Yep. Oh, you got one?
Just a quick one, Rick. You managed to get some really nice funding from Queensland government with Complex Orebodies going to the next year and perhaps beyond. How do you see the mix and the involvement with government opportunities for running projects?
Well, we'll be continuing next year to work closely with the Queensland government. And on a number of the projects, we're also now, we also now have support from the federal government, from Geoscience Australia. That's a project that started this year. That's working on the mine waste side of things. And in a couple of different areas, we're talking to I've already got a microphone, some of the other surveys, so Northern Territory, New South Wales. So obviously it's an area, particularly mine waste, but some of the other aspects as well are something that's of great interest to governments right now. So, and increasingly companies. So. All right, well, the last item this afternoon was perfect timing. Look at that, 15:40. We have a panel, yet another panel, and perhaps foolishly, Neil, Lisa, and who was the last person who agreed to? Oh yes, Andre agreed to be on the last panel. And so could you all come up, please?
one of the things that's happened in the last little while that we didn't previously have available to us was an expert in deep mining geoscience. But I have had it pointed out to me by quite a few people that if we're working on trying to work on technologies and approaches that could potentially lower footprints, why on earth aren't we working in deep mining geoscience? So with that, I was going to ask Andre Van Aast to introduce himself, and maybe could you tell us a little bit about the new yourself and the new deep mining geoscience program?
All right. So, well, a little bit about myself. Yeah, I've been in mostly in mass mining underground for my career. The last 30 years, I've been with Rio for a good 20 of those. Initially started with diamond mines with De Beers, and because of the caving expertise, we built the first block cave in Australia, and then been with Rio ever since. So yeah, I have had underground experience, I guess, mining experience, and especially caving experience, mass mining experience, different types of mass mine stopes or caving, mostly going, obviously all the caving seems to be going deeper and deeper. So from a deep mining point of view, it's not South African gold mine, 5 kilometers deep mining, although I've done at least 2 kilometers, but not mass mining. So that's my sort of background. It's mostly in geomechanics, by the way, not geology. I don't know much about geology. Well, I do, but I don't. I more care about how to break it and how to build it and fix it than what it's made out of. So, and then trying to get it out. And so, Rick, I'm not sure if I've answered all your questions. Is there anything else?
The other question I asked you was whether you'd be able to just tell us
about
a little bit about the new,
of course.
the new program, to the extent you've decided.
Well, look, it's early days, but it's clear to me that you know, where we were going in deep mass mining is that we can't keep on doing the same thing. So to date, we've been cutting edge in the mass mining underground space. We've been going deeper, but we've been taking, if you like, all of our cutting and pasting tools of mine design and just been going deeper and, you know, touching wood. And to be honest, I wouldn't say we haven't been successful, but I don't think if what the metric is successful, it's perhaps let's just say we're getting more complicated. And obviously stress and strength is the big issue for us. As we go deeper, stress is increased, but our rock masses are not, you know, in fact, they're decreasing many times. So the challenge with our deep mining, where I'd like to see deep mining go, is how do we extract it? It's all very well that we find it, but how do we get it out of the ground? So from that point of view, I think that a lot of the different areas that we want to cover in deep mining will be things like better characterization of geoscience type mine design criteria, if you like. Not just geology, geomechanics, water, and all these things that help us use all the data sets quickly and efficiently. Because I mean, it takes just if you think about a deep mine, it takes a couple of months to drill a deep hole. We can't be waiting for 10 years like we often are, or plus, just to get the data. So we need to be smarter about integrating. We need more data faster and integrating all that data and being able to come up with a solid, reliable mine design model. So there's a lot of that. Also, in terms of the governance, and we'd like to look at how do we truly assess the risk of deep mining and factoring that into the financial mine evaluation models like JORC, but only JORC for deep people and deep mines and including geomechanics. Things like mass mines, what would the mass mines look like, investigating different layouts and mining options, and looking at if we did go with things like caves, how is the mass flow of material within those caves influenced by stress? You know, things we've never really done. And all of our empirical design methodologies have all been based on near surface or shallower type deposits. So we need to really test some of our design criteria and the methods that we use to characterize deposits and build mines is really, if you like, beyond, I think, beyond what we really know. Yeah. And we've been lucky so far, if I can put it that way. And then obviously we need to upskill. So we're going deeper. There's a lot more, there's a lot of complexities. You know, I reckon it's pretty easy to just dig a hole from surface. My pit brothers don't agree with me, but anyway, I think it is. I mean, how hard is it to dig a hole? But when you go dig all the way down and try and get it out, that's twice as hard and complicated. So we actually don't have the engineers. One of the biggest projects I've been working on is educating Mongolians on geomechanics. We don't have geotechnical engineers that much. So we're taking the geologists, we're teaching them math, and we're taking the, oh, I'm just kidding, Rick, you know, but we're taking, you know, we're taking all sorts of, we're taking all these different people, and we're giving them a quick, sort of just raising the we've in fact in Mongolian University have completely changed the mining curriculum. We've been part of that process to fast track all the disciplines into filling gaps that, and I think that's the future where we're going to get. I hired 100 geotechnical engineers for one mine. I don't even think Australia has 100 geotechnical engineers, you know, so they might do. But the point is that as we go bigger and deeper, we need to get skills that we don't necessarily have. And let's face it, mining's not high on the young people's list of careers at this stage. They figure it out later, but you know, we need to be able to have programs in place that can take professionals and I guess so sorry for waffling on, Rick, but that's sort of the breadth of what we're trying to do is get into research some of the deep mining technologies and how we might do things, and then also upskill. So that's, I guess, what I was thinking.
Thanks very much, Andre. Neil, I think that, I hope this isn't too nasty a question, but it's regarding sort of water in the mining industry more generally, which I think, well, you disagree with me, but I keep hearing and sort of see that it's probably of all the things that we're going to, I mean, we're not really going to run into trouble on supply of a lot of metals, but I guess there's a good chance we're going to run into problem in supply of clean water. Maybe, but correct me if I'm wrong. But I guess my question is regarding water in the mining industry. You know, how good could it be in 2050 if we do a good job from here, but how bad could it be if we don't? Is that probably a terrible question?
Well, I think the fact is that good practice is out there. I mean, there's examples of good practice. There's good practice guides. And I think most of the problems we have at the moment is because good practice isn't followed very well. But partly that's a legacy issue. I mean, I think things are improving. A lot of the world is lagging way behind. So a lot of the really bad news stories, it's pretty obvious why that's happening. Because they don't have the, for some reason, the companies don't have the incentive to employ good practice. We don't even have the capacity in Australia, just like you said, for deep mining. I mean, it's complex. Things like the interaction between the geology, the geomechanics, the water, the groundwater, and that requires skilled people to assess these problems. So we even have that problem in Australia, but in many countries, an even more basic problem about capacity. Governance is another issue. I mean, places like, well, many countries, you know, there's even Peru, which is more advanced than other countries. They have some basic water governance issues that are pretty standard here, but not yet over there. How bad could it be? Well, there's plenty of examples, I think, of really sad destruction of catchments, and that take decades, if not hundreds of years to recover from.
Great. All right. Thanks very much. I'll go on to Lisa. One of the themes that we identified early on or talked about early on was around removal of arsenic and other deleterious elements from the mining value chain. And I know that's something that we've done work on here previously, and up until recently had tried without an enormous amount of success to actually get some projects going. But I was just going to ask you if you could give a general update on where we are with projects in that area, because I know we've had some, we're now kind of getting some initiatives going that sound very encouraging.
Yeah, thank you, Eric. It's a very good question. The problem with the presence of deleterious minerals in ores is not new. They've always been around. And the solution to all of those problems up to now has been to ignore it, to blend it out, or to deny that it exists. As long as there have been ways to get around having to tackle the problem has essentially been swept under the carpet. We are only now in the last couple of years getting to the point where companies are even willing to admit that they have arsenic in their ores, despite significant evidence to the contrary. Just to get a company to say out loud in a confidential setting that, yes, we have an arsenic problem, and to even admit the grades of arsenic in their ores has been unheard of. And so in the last couple of years, we've gotten to what when people are admitting it, but admitting it in private and not willing to make that public, because I guess that has a huge effect on share prices and such like things. And now we are getting to a point where the usual solutions were just blend it out and send it to China where the penalties are lower, people are starting to come to the conclusion that's no longer viable. So whereas we've had plenty of conversations before about the potential of maybe going forward with something, we are now having actual projects where we are being asked to look into, well, what are the options? What are the options that are available to us? And well, our friends from MMG are one of those people. Might as well do a shout out to Mario once more, to actually start looking into it openly and saying, yes, the problem is out there. Let's see what is available. And hopefully what will come out of work of this nature is that, yes, there are solutions, and we all know that those solutions will need further work and further refinement. And hopefully we are going to be there to assist with that, along with other experts in the area who have been working on this for a long time, with possibly some solutions that are already ready and waiting to be implemented. But as we know, we've been working on flotation for 100 years, and yet we still need ways of improving it. There's no such thing as a ready-made solution for anything in this business. And hopefully we're going to start seeing more and more companies follow that example and start to become a lot more open and honest about the presence of deleterious elements in their ore bodies, and we'll start to see a lot more progress being made in this area.
Thanks. And pass it off to Mario, please. Not Mario, sorry. Sorry, Andre. Yeah. Oh, it's been a long day. This is so I've heard from a number, had discussions, chats with quite a few people talking about sedimentary basins lying above potentially buried ore bodies, geothermal gradients, stress orientations, and so on, as determinants of the depth to which you can mine by underground mass mining. And I guess my question is, would it be possible to make an Australian, or even if you had the right information, this would be harder probably, a world map of deep mining amenability, like where a map that somebody could go to and say, okay, well, I can't do deep underground mass mining here at all. Here I could go to 1,000 meters. Here I could go to 2,000 meters. Is that something that is feasible?
Yeah, I guess it is, except that I mean, I've been working on mines that are looking at mass mines down to 2 kilometers, and we still haven't said that it's not feasible. We're looking at ways of trying to make it happen, and I guess that's partly what I'd be looking at. But is it feasible? I think we can certainly come up with some clear criteria over which would have a higher risk, perhaps. So we could have a risk map of mines, and based on certain criteria say, well, because of this, it's a high risk. But to say it's not viable, or that, I'm not sure we want to say that yet, because there's always ways of tackling things with new technologies and so on. And I don't think, especially in the mass mining space, I don't think we've exhausted the options looking at technologies and methodologies and new technology that that allow us to go that extra, to reduce that risk, and allow us to go that extra depth. So I'm not. Yeah, that's. So
it's more just how much you want to pay.
Well, it's not just to pay. It's if I look at some of the things, for example, one of my pet peeves is that if we go deeper, many mines that are forced into it, it's like a burning platform. If you look at the South African gold mines, they changed the way they mined completely in the 50s and so on to be able to accommodate stress at depth, and they've done it successfully. Who thought we would have mined at 5 kilometers or whatever? But part of that, for example, is the size of a tunnel. So what drives the size of a tunnel in a mass mine is to try and get the biggest piece of equipment you can to move. You need 20 tons of machine to move 10 tons of ore, 12 tons of ore. It just doesn't add up, does it? From then, so if we could find more novel ways of moving large quantities of ore, that doesn't mean a big machine, for example, and a smaller tunnel that can handle stress. Well, suddenly that opens up the whole game completely. If we could reduce the tunnel size, we get away from a lot of issues around stress. And if we could just get the ore, part of the reason we don't do that is because we need a big really great big loader and a big truck, but we don't. But we shouldn't have. There are other methodologies. So how do we do it smarter?
So if we had smaller, cheaper, more standardized trucks.
Well, it's not necessarily trucks or loaders, but different technologies. It would be some form of extraction. There's various technologies, like in the old days used to use an old scraper drifter that had a cable on a bucket and just used to drag the saw. Now let's not say that's not a great new technology, but maybe something of that form, but more would go a long way to eliminating the need of dirty great big tunnels that we can't keep open. So that's an example of that. Just as an example, anyway.
Sure. Great. Thanks, Neil. The one thing I wanted to ask you was, obviously, I think the project that you guys are doing in Chile is having a big impact, and it's very exciting. What else can we be doing in the water area to make impact on the sort of central problem in the Complex Orebodies program around, I guess, removing or addressing challenges that stop mines from being able to be put into production? Is there something else we can be doing, focusing in the water space that we're not doing?
Well, I think water is largely connected with all the other issues. So probably the most obvious ways to address the water shortage problem are the more efficient mining, perhaps deeper mining, so it's disconnected from the surface, addressing the social issues and frameworks for developing some kind of shared vision of the benefits of mining. In terms of what we can do on the technical side, I think there is new opportunities from the energy transition and revolution with renewable energies. The cleaner our energy sources and the lower cost our energy sources, the more and more water we can recover from mine wastes, and the further we can transfer water at low cost. So, I think if some of the projections of reductions in energy costs come to fruition, it means we will be able to pump, treat seawater or other dirty water and transfer it further and potentially open up new mining regions. We did make some assumptions about future energy costs in our Chile project, and surprisingly, we significantly underestimated the cost this year. For some reason, costs have gone up a bit rather than down, despite the projections in Chile. I'm not sure what it's like around the rest of the world, but it's very connected. Water is very connected with energy from the technical viewpoint. So the more we can do with energy, the more we can do with water.
Thanks.
Well, we did have a conversation at lunchtime there. There is some very interesting synergies between new energy sources and water. And one, of course, is hydrogen, because hydrogen is not only an energy source, but it's a water source as well. So we had this crazy idea that rather than pump up water from the sea up to the mines, if you could pump hydrogen up instead, then every 2 parts hydrogen, you get 18 parts water.
Yeah. There's plenty of oxygen about, I guess. So, yeah. Thanks for that, Lisa. We had a good, I think, discussion earlier on about the impacts of and some of the positive aspects and I guess areas of learning for the Azok Lake project. And I know that we had recently had a similar discussion and feedback session with the sponsors of our coarse particle flotation research project. And so I was just going to ask you about what the feedback was generally. I won't ask you to remember all the specifics.
You're so putting me on the spot right now.
Yeah.
The feedback, I think, rather than going into the specific feedback that all of the sponsors had given us in a confidential setting, I will reflect back on the feedback that we got from one of our sponsors, Ronald Cappies, during a panel during the Flotation 21 conference, which she said openly and out loud, and I have no compunction with sharing, is that I think she highlighted the importance of her being able to work with institutions like ours, where the mineral company or the end user does not act as a source of funding, but has a specific role as a technical collaborator. And that is exactly what we've seen in the Azok Lake project. And this is exactly what has been referred to as one of the key drivers for the success of that particular project. And I certainly see that in our coarse particle collaborative project, where I would say the key factor for the success of the project as it's been so far was not the fact that we got money, was the fact that we have the experience of 9 end users in the room, all giving us feedback about what is the problem that needs to be solved, what are the aspects of the problem that need to be focused on, and oftentimes providing us with suggestions and ways to find a solution. In other words, those wonderful people they're not just a bank to us. They are colleagues. They are our technical collaborators. And that is what I think is the most important aspect of it all.
Great, thanks. Before I go on to the next sort of set of questions, I wanted to open up to the floor to see if anyone had any questions or comments, anything they wanted to bring up. And I'll check the while I'm doing that. While you guys are thinking of your great questions, I'll check and see if there's anything. I see things in the chat, but nothing in the. We do have people who still faithfully online, but nobody's asked a question. So.
I suppose we had a bit of a conversation at the break where, and I wanted to ask you on the previous one, we've done that really good work in Chile, but there are equal opportunities in Queensland to do something very, very similar. And I think there have been some projects that Claire's put forward, and I don't know if you want to just comment on those, where just having a look at regional water management, particularly in Queensland and the Bowen Basin. I don't know if it's possible just to comment on that.
You'll need a microphone.
Yeah, thanks, Neville. The issue in Queensland we're interested in is more on mine closure, closed mines, and the water resources opportunities that presents, because we're going to have many, many pits which accumulate water, and there is a risk that that water will essentially just evaporate and go to waste or become a liability in the pit. And yet there's much fertile soil around, and the only reason why that fertile soil isn't being productively used is lack of water. So we've been looking at the synergies, we've been overlaying the locations of the mine pits with productive agricultural land, looking at the potential for carbon sequestration that would provide in the soil, the possibility of producing organic crops with higher value, and the need for interconnections as well, rather than just the farmland in the vicinity of the pit benefiting from that, what infrastructure would be needed. So we're kind of at the beginning of that. There's two things going on taking that forward. There's a continuing development of a CRC funded project in partnership with funders, UWA, CSIRO, and others. So that's under discussion. And then we're collaborating with QAFI with some strategic funding from the university, and also with some industry funding to look at a big case study around one of the mines that's coming up for closure. And that's specifically working with a farmer who's interested in organic farming and using the operational water from the mine, surplus operational water, but also the post-closure water. Yeah. Yeah.
Any other questions from anyone? I'm just reading the room here, and I'm going to give us all a 10-minute early mark, I think. I'm just thinking it's been a long day. Everybody's contributed very well. I think thanks everyone for coming. And I think I might draw this to a close and thank all the speakers today, everyone who participated in panels and contributed online or in person. And thanks everyone for all your hard work this year on the Complex Orebodies program, and here's to an even better year next year. Oh, did you want to say something, Neville? Yeah, okay.
I can't let Rick walk away without at least saying thank you, Rick. So Rick, thanks. I think we all appreciate the effort and the time you put into making this program so successful from the beginning. And we spoke about Steve's capability as herding cats. I think you are the master cat herderer, and that we all are learning from you. So Rick, thank you very much. And thanks for putting this all together and making sure all of the technology works. I was waiting for something to go wrong, because every time I've done something, it's been a disaster, and you saved me. So thank you. And to those that are online, well done.
Except the Nikon webcam utility, my new camera, and it's failed me. But anyway, we'll work it out. It'll be better next time. But I'm glad you said that, because what it reminds me is that when you said thank you for putting all this on, what I have to say is that it wasn't me. It was Marie-Louise and Kathy and Melinda, of course. So I'd really like to thank all of them for their hard work in doing a lot of the logistics for this, not me. So well done.